are important considerations. The atmosphere that surrounds the Earth is relatively thin. Although it extends several 100,000 feet into space, about half of the total atmosphere is compressed below 3.5 miles. Many people have the false impression that the atmosphere is mostly comprised of oxygen, but in reality, only 21% of the total gas is oxygen. Nitrogen makes up most of our atmosphere, with carbon dioxide, argon, and other gases making up the remaining 1%. The atmosphere is made up of several basic layers, with the lowest layer being the troposphere. This layer slopes upward from about 20,000 feet at the poles to about 60,000 feet at the equator. Most of the weather which you will be concerned with will be found within this layer. Above the troposphere is a thin layer known as the tropopause, which acts as a lid on the troposphere, keeping most of the moisture within the layer below. The stratosphere extends to about 22 miles above the surface. The air within this layer is very dry and stable. Few cloud formations penetrate into this layer. Above the stratosphere are the mesosphere and the thermosphere. These layers have very little effect on the weather. The gases in the atmosphere contain molecules that are constantly in motion. As the air is heated, these molecules speed up, creating more space between them. The result is fewer molecules per given volume of air. When the air is cooled, the molecules become less active, meaning more can exist in a given volume of air. This cooler air is heavier and denser than the warmer air. The differences in air density are the basis for the movement and circulation of the atmosphere. To demonstrate this principle, suppose we have two rooms, one which contains cold, dense air, while the other has warmer, lighter air. When the door is opened, the air begins to mix. The heavier, colder air slides under the warmer air, creating a cold draft on the floor. As the cold air fills the bottom of the room, the warmer air replaces the colder air. On a larger scale, the draft created between the rooms is called wind. Air replacement due to these density changes drives our major weather systems. This density difference is due to the pattern of global heating. At the equator, light from the sun strikes the surface at an almost perpendicular angle. Near the poles, the surface of the Earth is largely turned sideways to the sun. This results in more atmosphere between the sun and the Earth at the poles. This greater amount of atmosphere cuts down the intensity of the sun's rays. Also, the same amount of light that would cover a given area on the equator is distributed over a far larger area at the poles. The result is less heating energy per square mile. As the sun's radiation heats the tropical areas of the Earth, the air becomes less dense and rises. Because less dense air does not exert as much pressure, a permanent low-pressure area forms near the equator. Nearing the top of the troposphere, the warm air is displaced sideways, away from the equator. The air continues northward and southward, slowly becoming cooler until it begins to descend near the poles. This colder descending air creates a permanent high-pressure area near the poles. The air then returns along the surface, back toward the equatorial areas, to replace the rising air. If the Earth didn't rotate, there would be a continuous circulation pattern from the polar highs to the equatorial low. But because it does, this theoretical one-cell circulation pattern becomes a three-cell pattern. In this circulation pattern, the air near the equator still rises and flows toward the pole. But this branch, known as the Hadley cell, only reaches about 30 degrees north. Here it combines with sinking air from the Ferrel cell that corresponds with a semi-permanent subtropical high-pressure area. Near 60 degrees north, the warm surface winds of the Ferrel cell and the cold winds of the polar cell collide, rising to produce an area of low pressure. In addition, these airflow patterns are affected by Coriolis force. In order to better explain how Coriolis works, let's use the example of two ball players attempting to play catch on a merry-go-round. As the pitcher throws the ball, it travels in a straight line. But not to the catcher. To the thrower's perspective, some force seems to be turning the ball to the right. This same situation applies to air as it flows from the North Pole to the equator. Because of the Earth's rotation, the wind seems to be deflected to the right. This apparent rotation is called Coriolis force. Atmospheric pressure, or the concentration of air molecules over a given area, is measured in terms of inches of mercury, or millibars. 1 inch of mercury is equivalent to approximately 34 millibars. The measurement of pressure is done with the use of a barometer. This instrument is nothing more than a partial vacuum within a glass tube containing mercury. As the pressure of the air exerts a force on the container of mercury, the mercury will rise. The average atmospheric pressure of the Earth will make the mercury rise 1,013.2 millibars, or 29.92 inches. This measurement is considered to be standard pressure. During periods of higher atmospheric pressure, the force exerted upon the mercury is greater, which forces the mercury to rise. The reverse happens during periods of lower than standard pressure. If we imagine standard air pressure as a plane, we can visualize the relationship between air masses with different densities. On the left is a high-pressure system, or a mass of denser than standard air. It is more dense at the center of the mass. On the right is a low-pressure system, or a mass of less dense air. Pressure changes occur more rapidly directly between the center of the high and the center of the low. As we rotate the image to a top view, we can draw lines around the areas that appear to have the same height, or in this case, the same amount of atmospheric pressure. These lines are called isobars, and they are drawn on weather maps to represent areas of equal pressure. By using these lines, you can determine the position of high and low pressure areas. You can also tell how large or severe they are by the number of lines and how they are placed. Notice how the isobars are closest together directly between the high and the low. The closer the lines, the stronger the pressure gradient. Air from a high pressure area will flow directly toward a low with a force which relates to the pressure gradient. If the Earth didn't rotate, highs and lows would exchange wind directly in this manner. However, Coriolis force from the rotation of the Earth is also acting on these systems. As winds spill off a high-pressure area in the northern hemisphere, they are deflected to the right. This results in a clockwise flow around a high and a counterclockwise flow around a low. As the wind is driven around these systems, the air closest to the surface is slowed by the friction of the ground. When this happens, the Coriolis force is diminished until the pressure gradient force becomes greater. The resulting wind tends to flow across the isobars toward areas of lower pressure. At altitude where airflow is not affected by the surface friction, the wind continues to flow parallel to the isobars. In addition to creating large patterns of wind around highs and lows, differences in atmospheric density can cause wind flow on a local level as well. In areas near the ocean or other large bodies of water, local changes in heating and atmospheric density can cause daily wind flow patterns. During the day, water slowly absorbs heat. On the nearby land, the sun's radiation only penetrates a few inches into the soil. The land surface heats up much quicker than the water. As the air over the land warms up and begins to rise, air over the water is being cooled down because of the cooler surface of the ocean. The cool air then flows inland to replace the rising warm air. This produces a sea breeze flowing inland from the ocean. During the night, the land cools very quickly. The air above the landmass begins to cool and sink. The ocean, now warmer than the land, begins to warm the air above it, causing the air to rise. The flow of the cycle now reverses, and in the evening, a land breeze will be experienced. Local wind patterns can also form as the result of mountainous terrain. One of these is a foehn wind, which occurs when there is a mass of cold, dense air near the top of a mountain range. As the air pushes over the top of the range, the cold air begins to descend down the other side. As this air accelerates and replaces the warmer air beneath it, it begins to compress and warm up. As the air heats, it will eventually become warmer than the air it is replacing. This causes the atmosphere at the bottom of the hill to become warmer. These winds can become very strong, with gusts exceeding 120 miles per hour. In the Rocky Mountains, they are called Chinooks. In the Sierra Nevada mountains, they are the Santa Ana winds. Regardless of their names, these winds can produce large amounts of damage and are hazardous to aircraft, both in the air and on the ground. They can occur during what would normally be perfectly good VFR weather, and is one of the reasons surface wind reports are important to you when receiving a weather briefing. We have seen how heating and the differences in air density can produce wind. The other major force in the formation of weather is moisture. Moisture occurs on our planet as a solid, a liquid, and a gas. Within these states, it can take many forms. We see moisture as clouds, as rain, hail, or as snow, ice, or water. Dew and frost are also forms of moisture. How water changes back and forth from state to state is very important to the formation of weather. We have all experienced the effects of evaporation, such as water evaporating from a lake. When water turns from a liquid to a vapor, the process requires heat. This heat energy is drawn from any available nearby source and is stored by the vapor. When the water vapor is returned to a liquid through the process of condensation, the latent heat that was stored during evaporation is now released. The heat exchange during evaporation and condensation is a major factor in the vertical movement of air columns. Thunderstorms, for example, can be developed by this force. Originally, the air begins to rise through a force such as the sun heating the surface, which in turn warms the air above it. As this warm air cools and eventually condenses, the latent heat released from condensation will, under the right conditions, continue or increase the strength of the updraft. If this process continues, a thunderstorm can develop. In vapor form, molecules of water exist between other molecules contained in the atmosphere. When the air is warm, more room exists between the molecules of air. Therefore, more water molecules can squeeze between the air molecules. When the air is colder and the air molecules are closer together, less water vapor can fit between the already close air molecules. For this reason, cold air cannot hold as much water as warmer air. Dew point is the temperature at which an air mass becomes completely saturated with water vapor. In other words, it will hold as much water as the temperature will allow. When an air mass becomes completely saturated, condensation occurs. Let's say that we have an air mass with a temperature of 55 degrees Fahrenheit. If the dew point is also 55 degrees, then the air is 100% saturated. If condensation nuclei are present, then condensation will occur. Clouds, fog, and dew are all forms of condensation. When water that is formed on the condensation nuclei becomes too heavy for the atmosphere to support, then precipitation occurs. Since the moisture content in an air mass is relatively constant, the air mass must usually undergo some form of cooling in order for condensation to occur. For example, if the air is 50% saturated at 55 degrees, then the air must be cooled to about 37 degrees in order for condensation to occur. When the temperature reaches 37 degrees, this air mass will be 100% saturated. Weather is something that we must deal with daily as pilots. It is constantly changing and infinitely complex. Knowing the basic driving and manipulating forces of our Earth's weather patterns will help you to understand the more detailed conditions and concepts that will be introduced in the following weather sections. Being able to understand the concepts of weather development will not only help you understand the current conditions, but will also help you anticipate future changes as well.
It looks looks like it's going to be a cold one today. An Arctic cold front moved into our area around 3 this morning and has already dropped 3 to 4 inches in some parts of the city. The air mass associated with this front is stable, and with all the moisture that's being pushed up from the Gulf, we're in for snow the rest of the day and possibly tomorrow.
Every day, all over the world, people are dealing with the effects of the weather. In the previous section, we saw how the forces of air density, Coriolis, temperature, and moisture worked independently of each other. In this section, you'll see how they interact to produce the weather phenomena we see every day. The type of weather we experience is, in part, related to whether or not air rises or falls in relation to the surrounding air. The term used to measure how much relative resistance an air mass has to this vertical movement is called stability. A stable air mass, for example, resists vertical motion. This inhibits large cloud formation, heavy precipitation, and severe weather. An unstable air mass, on the other hand, has the potential for significant cloud development, turbulence, and hazardous weather. The weather in the tropics is a good example of unstable air. With its warm temperatures and high humidity, daily thunderstorms are commonplace. Air mass stability plays a large role in the development of weather. We can best see this role in the development of clouds. There are 2 basic types of clouds, cumulus and stratus. Cumulus clouds are formed by rising currents of air, which gives them a piled up or bunched appearance. They warn of unstable air, turbulence, and showery precipitation. Visibility outside the precipitation is usually good. In air masses with a high amount of stability, stratus clouds may form. Resisting vertical movement, these clouds form in smooth layers and often extend over large distances. Since the air is stable, flight near stratus clouds is normally smooth. Precipitation from these clouds can be continuous and last for several hours or even days at a time. The visibility associated with stratus clouds is usually poor. In addition, clouds can further be grouped into high clouds, middle clouds, low clouds, and clouds with extensive vertical development. Cirrostratus, cirrocumulus, and cirrus clouds are examples of high clouds. They are composed almost entirely of ice crystals and seldom pose hazards to pilots. Most names of middle clouds contain the prefix alto, such as altostratus or altocumulus. These clouds are composed of water, ice crystals, or supercooled water, which is water that has been cooled below its freezing point but is still in a liquid state. They can contain moderate turbulence and potentially severe icing. A cloud with a name containing the prefix nimbo or the suffix nimbus contains a large quantity of moisture. A nimbostratus cloud, for example, can produce widespread areas of snow or rain. While classified as a middle cloud, the nimbostratus cloud can merge into the clouds formed at low altitudes. A cloud which can be very deceptive to pilots is the lenticular cloud. This lens-shaped cloud may form over mountain crests during high wind conditions. Even though it looks smooth and serene, it is, in reality, a good indication of heavy turbulence and should be avoided. The low clouds form near the surface and extend to around 6,500 feet. Clouds within this group include the stratus, stratocumulus, and fair weather cumulus clouds. The thunderstorm, or cumulonimbus cloud, is an example of a cloud with extensive vertical development. This type of cloud can have its base as low as 1,000 feet and extend up to the heights associated with high clouds. Flight near a thunderstorm can be extremely dangerous. These hazards will be discussed in the next section. So far, we have talked about the stability of an air mass and the types of clouds which can form if the air mass is stable or unstable. But how and where do these air masses begin, and what happens to them as they move? As we discussed earlier, the global circulation patterns form high and low pressure areas. The high-pressure areas, located at the poles and in the tropical areas, act as source regions for air masses. If an air mass forms over water, it is further classified as maritime. This type of air mass will usually contain more moisture than a continental air mass, which forms over the land. As an air mass leaves its source region, it is modified. The amount of modification depends on the speed of the air mass, the nature of the region over which it is traveling, and the difference in temperature between the air mass and the region. As an air mass moves, it comes in contact with other air masses of different properties. Since air masses with different temperatures and pressures do not mix very well, their boundary forms a front. As you fly across a front, you may experience discontinuities, which are rapid changes in atmospheric conditions. These include temperature, wind, and pressure. Temperature is probably the most easily noticed change, but the two which should concern you more are wind and pressure. An undetected change in the wind could cause you to drift off course inadvertently. When flying through a front, you should expect a wind shift and adjust your navigation accordingly. Since there is usually a pressure change when you cross a front, you should reset your altimeter to the correct setting to avoid being higher or lower than the indicated altitude. Fronts are defined by the type of air mass that is in the overtaking position. In other words, if a colder air mass is overtaking a warmer one, then the resulting front is called a cold front. This definition is relative, though, because a cold front can be any temperature, as long as it is cooler than the air mass it is overtaking. As a cold front moves, it replaces warmer air at the surface. Since colder air is denser, it pushes the warmer air aloft. If this warmer air is relatively dry and stable, stratiform clouds form in the vicinity of the advancing cold front. If the warmer air is relatively moist and unstable, cumuliform clouds may form along the front. A rapidly moving cold front can create thunderstorms many miles ahead of the frontal boundary. A line of these thunderstorms parallel to the front is called a squall line and can contain violent weather. The thunderstorms in a squall line can grow to 65,000 feet and can be especially violent. These storms often produce heavy rain, large hail, and even tornadoes. In contrast to a fast-moving front, the slope of a slow-moving cold front is not as steep and the lifting action is not as great. Therefore, the weather is less severe. When a warmer air mass overtakes a colder one, a warm front exists. Because of the difference in relative densities, the warm air will slowly slide over the colder air. This can result in very little vertical air movement. If enough moisture is present and the colder air mass is relatively stable, stratiform clouds usually form. These clouds may extend for many miles ahead of the front. However, there may be some cumulus clouds present in the form of embedded thunderstorms if unstable air is present. The weather associated with a warm front usually includes low ceilings, fog, and a subsequent reduction in visibility. When two air masses of relatively equal strength collide, a stationary front may form. Here, there is very little movement. The weather associated with this front can vary depending upon the temperature, moisture content, and stability of the air masses. It is usually a mixture of that found with both warm and cold fronts. One of the most complicated frontal systems is the occluded front. In this case, a fast-moving cold front is overtaking a slower-moving warm front. There are two types of occluded fronts. The one shown here is a warm front occlusion because the air ahead of the warm front is colder than the overtaking cool air mass. Of the two types of occlusions, this one produces the more severe weather. The other type is a cold front occlusion. Here, the cold air is replacing cool air at the surface. This type of occlusion generally doesn't produce weather as poor as a warm front occlusion. However, like the warm front occlusion, the weather associated with it is hard to predict and can produce a wide variety of weather considered dangerous to most general aviation aircraft. With weather patterns constantly changing, it is important to understand the factors behind their development and to get a good pre-flight weather briefing before flying. In the next section, we'll take a look at how these weather systems can be hazardous to flying and what you can do to predict these conditions and avoid them. Weather hazards come in many forms. Some are clearly visible, while others may be encountered unexpectedly. In this section, we'll look at some of the common hazards and discuss how you can avoid them. The thunderstorm is a weather phenomenon which is capable of producing very violent conditions. Thunderstorms can develop rapidly, and the hazards associated with them can exist for several miles beyond the storm itself. 3 atmospheric conditions are necessary for their formation. The first is unstable air, which allows for extensive vertical development. Second, there must be some type of lifting force, such as convection. Finally, moisture must be present. A thunderstorm passes through 3 stages: cumulus, mature, and dissipating. The cumulus stage is characterized by updrafts, which may extend from near the Earth's surface to several thousand feet above the visible cloud. Also, during this stage, water droplets form into raindrops. However, instead of falling to the Earth as precipitation, they are suspended in the cloud by the updrafts. The second, or mature stage, begins as the raindrops begin to fall to Earth. You can expect the most violent weather to occur during this phase. At this time, the raindrops have grown so large that the updrafts can no longer support them. As they fall, they pull air with them, creating downdrafts, which may exceed 2,500 feet per minute. As the downdrafts reach the surface, they spread out, creating strong, gusty surface winds. The dissipating stage begins when the cell becomes predominantly downdrafts. During this stage, the intensity of the precipitation decreases. It is also during this stage that the upper-level winds often blow the top of the cloud downwind, giving it an anvil appearance. However, this does not necessarily mean that the storm is over. Severe weather could continue well after the anvil forms. While thunderstorms usually have similar physical features, they can differ in intensity, degree of development, and associated weather. Lightning is one of the weather hazards that always accompanies thunderstorms. Other hazards might include heavy rain, hail, turbulence and gusty surface winds, and even tornadoes. As you gain experience, you'll learn how weather limits your flying. But regardless of your experience, you should always avoid intentionally flying into or near thunderstorms. To do this, you must know where they exist or are likely to develop. You can determine this by checking weather reports and forecasts prior to departure and during your flight. If widespread thunderstorms are being reported, you might find it necessary to delay or cancel your flight. If you encounter thunderstorms while airborne, you should never attempt to fly over them. These clouds can build faster than your airplane is capable of climbing. Flying below the cloud can be just as hazardous because of the extreme turbulence produced by the downdrafts. And you shouldn't try to fly around a thunderstorm unless you can maintain at least 20 miles between it and yourself. If that isn't possible, it might become necessary to turn around or fly to an alternate and wait for the storm to pass. The turbulence associated with thunderstorms varies in intensity from light, annoying bumps to severe jolts that can damage your airplane and injure its occupants. To minimize its effect, slow to maneuvering speed or less. One form of turbulence, called wind shear, is a sudden shift in wind speed or direction. It can occur at any altitude and in a vertical or horizontal plane. Wind shear is often associated with a more serious phenomenon called microburst. A microburst is an intense, localized downdraft which descends from the base of a convective cloud. As the air reaches the surface, it spreads out in all directions, often forming in a circular motion. This circulation creates an area of severe horizontal and vertical wind shear. A wind shear is particularly dangerous when it's in the proximity of an airport. To show you what can happen, suppose you're taking off into a microburst. You would initially experience a headwind and an increase in performance. When the aircraft reaches the point where the wind shears to a tailwind, it experiences a severe decrease in performance which could lead to disastrous results. Some airports are equipped with a low-leveled wind shear alert system, which allows controllers to advise you of significant wind differences on the field. Whether or not this system is available, any time a thunderstorm is in the vicinity, you should anticipate the presence of a microburst. While most microbursts are associated with heavy precipitation, moisture does not have to be present. They sometimes occur in virga, or streamers of precipitation that trail behind clouds and evaporate before reaching the ground. If there is no precipitation, a ring of dust on the ground, or trees being blown in different directions may be your only indications. Do not take off or land at an airport when you suspect a microburst exists. If you are in the air, delay your landing or divert to another airport. Most microbursts will pass over an area within a few minutes. Another form of turbulence occurs near mountains. It develops when the air is stable and winds in excess of 40 knots are flowing horizontally over mountain ridges. However, some turbulence may develop when the winds blowing over the ridges exceed 25 knots. If the air is unstable, the air on the windward side of the ridge will probably be extremely turbulent. If there is enough moisture present, cumulus clouds and possibly thunderstorms may develop. As the wind crosses the ridge, it spills down the leeward side. This may create violent downdrafts which could exceed the climb capability of your aircraft. If the air is stable, the wind flow will be smooth on the windward side. As it crosses the mountain, it tends to flow in layers or waves. The crests of these waves are often marked by lens-shaped clouds. These clouds are called standing lenticulars because they form in the updrafts and dissipate in the downdrafts, giving them an appearance of remaining stationary. Anytime this type of cloud is present, you should expect turbulent conditions. If you fly at airports used by large aircraft, you should be alert for another type of turbulence called wake turbulence. This type of turbulence occurs when a large airplane is generating lift and is most pronounced at low airspeeds and high angles of attack, such as when taking off or landing. Although it eventually dissipates, wake turbulence can persist for several minutes. If you encounter it as you're attempting to take off or land, the results could be disastrous. Aircraft that has just taken off, you should lift off before the airplane's rotation point and remain above its flight path. If a light crosswind is present, you should fly upwind of the large aircraft's flight path. And finally, if you're departing after a large aircraft has landed, make sure you lift off at a point beyond the touchdown point. Another weather hazard you should be familiar with is structural icing. Since it occurs only in visible moisture when the aircraft surface is at or below freezing, you're unlikely to encounter structural icing until you're instrument rated. The major reason icing is dangerous is because it changes the shape of the airfoil and destroys its lift. It can also increase the weight of the airplane and restrict control movements. Frost is a related element that you are more likely to encounter as a VFR pilot. Like icing, it can be hazardous because it interferes with the smooth airflow over the wings, resulting in a loss of lift. You should never take off unless you have removed all frost and other ice formation. As a VFR pilot, virtually all of your flying will be done with reference to the ground. When your visibility is restricted by elements such as haze, smog, smoke, fog, blowing dust, snow, or volcanic smoke and ash, you may have problems determining your position. Fog is one of the most persistent weather hazards and is frequently the cause of surface visibilities being less than 3 miles. It can form rapidly, changing from VFR to IFR conditions in just a few minutes. Anytime you have high humidity, a small temperature dew point spread, and light surface winds, you should anticipate fog and have an alternate course of action if it does occur. Although volcanic eruptions are not a common occurrence, volcanic smoke and ash can pose an extreme flight hazard. In addition to reducing flight visibility, volcanic ash can cause compressor stalls and flameouts in jet engines. In piston-powered aircraft, it can also cause severe damage or engine failure. Ash clouds are most dangerous close to the volcano when an eruption has just occurred. This is due to the large amount of ash particles, hot gases, and dust. Because volcanic ash is highly abrasive, control surfaces can be damaged and the pitot-static system and ventilation systems may become clogged. When volcanic material is injected into a stable atmosphere, the ash and smoke may be carried long distances by atmospheric winds. The gases and smaller particles spread out and may be very difficult to distinguish from an ordinary water or ice cloud. Currently, the National Weather Service monitors volcanic eruptions through pilot reports, radar, and satellite observations. Then, by using computer forecast models, the NWS forecasts ash cloud movements and provides subsequent advisories as required. If you observe a volcanic eruption, notify ATC. However, do not jeopardize flight safety to make a report. Immediately take evasive action by turning upwind to avoid entering the ash cloud. Don't attempt to fly through or climb above the cloud. When you are safely away and you can make your report to ATC, provide the location and altitude of the cloud, wind direction, and a description of the ash cloud and eruption. As you gain experience, you'll learn to recognize hazardous weather conditions. In addition, you'll learn that with proper pre-flight planning, you can avoid areas of potentially dangerous weather before you encounter it in the air. In the next volume, we'll discuss the types of information which are available to you and how to interpret them. Many people believe predicting the future is a hazy, inexact process. For them, an accurate prediction depends on blind luck or good fortune. However, relying on luck to predict the weather for your flight is not wise. As a pilot, you must rely on good forecasts. Fortunately, a number of methods with varying accuracies have been developed to help you anticipate weather conditions. Have you left your house in the morning for work, noticed the nice weather, and determined it would still be nice later in the day? If so, you have made a persistence forecast. By assuming the existing weather conditions won't change during the day, you predict the weather in the afternoon will be as nice as it was in the morning. However, this method of forecasting is not reliable over long periods of time, usually not more than 1 or 2 hours. Trend forecasting predicts that, without interruption, a weather event, like a storm cell, will continue moving in the same direction and at the same speed it's currently moving. In this case, the storm will reach the airport in less than 2 hours if atmospheric conditions don't act to change its course and speed. Similar to persistence forecasts, trend forecasting is generally accurate for only a few hours. At times, predictions are based on the average historical weather for an area. Known as climatological forecasts, they are reliable in areas and times which enjoy little change in day-to-day conditions. For instance, San Francisco has a generally moderate climate and may receive less than 1 rainy day per month during the summer. The analog forecast also uses historical data for predictions. This method is useful in predicting the temperature for a given day. By combining past data for a certain day with prevailing weather conditions, a meteorologist can accurately predict the expected high or low temperature. One of the better ways to predict the weather is the meteorological forecast. A good meteorologist can reliably forecast out to 12 hours by using his knowledge of atmospheric processes. This type of forecast can be a valuable tool for pilots. Powerful computers and mathematical equations have increased forecast accuracy by modeling weather trends. The result is a numerical weather prediction. The computer runs one forecast model on top of another to determine their effects over time. Doing so produces a relatively accurate picture of future weather events. Regardless of the forecast you receive, you can be sure the information contained was collected and compiled with the help of numerous agencies. With thousands of land and sea-based reporting stations, large volumes of weather data can be collected and analyzed. Through the coordinated action of several agencies, including the World Meteorological Organization, National Weather Service, and numerous private organizations, weather information is disseminated for your use. Although the weather collection and dissemination network is extensive and thorough, it's not perfect. While forecasting accuracy continues to improve, long-term forecasts and short-term predictions of localized weather phenomena are still difficult to develop with reliability. Even though forecasters aren't always precise, the experience and skill they can provide you is superior to other methods of predicting the future. After all, when it comes to aviation weather, having the edge provided by a good forecast is better than taking your chances.
A weather check is not only an important part of your pre-flight planning, but is required for any flight not in the vicinity of an airport. A wide variety of weather reports and forecasts are available for pilots to use. Today, there are several ways you can access these reports and forecasts, including a personal visit to any flight service station, computer-based weather briefings, and weather reports by fax. Since the systems allow direct access to printed weather information, learning to decode actual reports and forecasts is just as important as ever. During this program, you'll become familiar with aviation routine weather reports, pilot weather reports, radar reports, terminal aerodrome forecasts or TAF, area forecasts, airmets, sigmets, convective sigmets, winds and temperatures aloft forecasts, and finally, notices to airmen or NOTAMs. Let's begin our discussion with a look at METAR, or Aviation Routine Weather Reports, which contain the latest reported hourly weather observations for various locations. The information for each reporting station is printed in a coded format beginning with the report type. Here, the word METAR represents a routine report. If SPECI is in this location, it indicates a special, non-routine METAR weather report, which means the report was issued at other than the regular time, and there has been a significant change in the weather since the last report. The next element contains the station identifier. Notice the METAR code uses the ICAO, International Civil Aviation Organization, 4-letter station identifier. The stations within the contiguous 48 states are prefixed with a K. Here, KDEN is the identifier for Denver. Following the station identifier are the date and time in Zulu of the weather observation. When a report is generated by an automated weather observation station that has no human intervention, the word auto will follow the date-time group. If a correction is made to a report, the abbreviation COR is substituted for the word auto. The remainder of the printout is dedicated to weather, beginning with wind. Surface wind readings make up this section. The wind direction is given first, followed by the wind speed in knots. Here, the wind is blowing from 330 degrees at 18 knots. Variations of wind speed are shown as gusts and are indicated with a G. In this example, the wind is from 290 degrees at 30 knots, gusting to 45 knots. If the wind direction is variable and the velocity is 6 knots or less, it is noted by the prefix VRB. Here, the wind is variable at 4 knots. When the wind direction varies by 60 degrees or more, a variable group consisting of the extremes in wind direction, separated by a V, will follow the prevailing wind group. In this example, the wind direction has varied from 290 to 360 degrees. A calm wind condition is indicated by 5 zeros followed by KT. The next element of the METAR report gives the visibility in statute miles. At Denver, the visibility is 1/2 statute mile. When runway visual range is reported, it is preceded by an R. The next 2 digits are the runway number, followed by the visual range measured in feet. Here, the RVR for runway 31 is 2,600 feet. The next section of the METAR report is the present weather at the time of the observation. The type of precipitation or the obscuring phenomena is shown in code and may be preceded by an intensity symbol, a proximity code, and a descriptor code. Intensity levels are shown as either a plus or minus symbol and only apply to the first type of precipitation reported. This example indicates that light rain is falling. The plus symbol denotes heavy rain, and no symbol indicates moderate intensity. When the reported meteorological conditions are between 5 and 10 statute miles of the usual point of observation, the code VC is used, indicating the reported weather is in the vicinity of the airport. 2-letter descriptors are used to provide even more information about precipitation and obscuring phenomena. Here, FG indicates that fog is the predominant obscuring phenomena. Other common descriptors are TS for thunderstorms, SH for showers, FZ for freezing, DR for low drifting, MI for shallow, and BC for patches. The common letters used to indicate precipitation and obstructions to visibility include RA for rain, DZ for drizzle, GR for hail, FU for smoke, and HZ for haze. Additional codes are listed in your manual. The next block is used to report sky conditions. The amount of coverage is reported in eighths of sky cover and is represented by different contractions. If the sky is clear, meaning there are no clouds visible to the observer, the report will contain the letters SKC. At automated stations, the abbreviation CLR is used to indicate no clouds below 12,000 feet are detected. The letters FEW in the METAR report mean up to 2/8 of the sky is covered by clouds. A scattered layer, or SCT, means that the clouds cover 3/8 through 4/8 of the sky. A heavier sky cover is referred to as broken and is indicated on the report with the letters BKN. In this case, the clouds are covering 5/8 through 7/8 of the sky. When OVC appears, the sky is reported as overcast, which means clouds completely cover the sky. When the sky is reported as broken or overcast, a ceiling is said to exist. The height of the cloud bases are reported with 3 digits measured in hundreds of feet above ground level. Here, the first layer is a scattered layer at 800 feet, with a second overcast layer at 1,000 feet. When the sky is obscured by a surface-based layer, the vertical visibility is reported. The letters VV indicate an indefinite ceiling, and the 3-digit number is the height in hundreds of feet. In this case, the vertical visibility is 400 feet. Cumulonimbus clouds or towering cumulus clouds are observed. The letters CB or TCU will follow the number representing the height of the cloud base. In this example, the observer has reported a scattered layer of towering cumulus at 1,500 feet. The next segment of the report gives the temperature and dew point in degrees Celsius. When these temperatures are below 0 degrees Celsius, they are preceded by an M. In this example, the temperature is 10 degrees Celsius and the dew point is -8 degrees Celsius. Altimeter settings are preceded by an A and reported in a 4-digit format in inches of mercury. Here, Denver's altimeter is reported as 29.901 inches of mercury. The last section of a METAR contains remarks and is identified by the contraction RMK. This section includes operationally significant weather, as well as the beginning and ending times of the specified weather phenomena. In this example, rain began at 35 minutes past the hour. At 55 minutes past the hour, the rain ended. Pilot weather reports, or PIREPs, also provide valuable information about current weather conditions and should be reviewed in a thorough weather briefing. No other observations are more timely than the ones made by a pilot. In fact, PIREPs provide the only means of directly observing cloud tops, icing, and turbulence. A PIREP is usually received and transmitted in a prescribed format. The letters UA identify the report as a routine PIREP, and UUA identifies an urgent PIREP. 2-letter codes differentiate each block within the report. For example, OV describes the location of the aircraft. TM tells you the time when the report was made. FL identifies the flight level. And TP tells you the type of aircraft flown. These first 5 blocks must be included in all PIREPs. The PIREP must contain at least one of several weather elements, also identified by 2-letter codes. These include SK for sky cover, WX for flight visibility and weather, TA for temperature, WV for wind, TB for turbulence, IC for icing, and RM for any remarks that might be included within a report. In printed form, PIREPs appear in this format. This sample PIREP from near Centennial Airport was issued as urgent. The aircraft was on the Denver 161 radial at 14 miles. The time of the report was 1939 Zulu, and the pilot was flying at 11,500 feet in a Mooney Mark 20. The pilot reported moderate to severe turbulence between 11,500 and 14,000 feet while en route from Farmington, New Mexico to Centennial Airport. Radar reports are another important source of weather information since they identify areas of precipitation at the time of the report. Each report can be divided into as many as 10 blocks of information. The first segment contains the location identifier and the time of the radar observation. This report is from Evansville and was taken at 1926 Zulu. The observation shows an area of echoes with 3/10 coverage consisting of light rain showers, which are decreasing in intensity. The next segment defines the boundaries of the area of precipitation using the azimuth and range from the reporting site. In this example, the points defining the area of echoes are 338 degrees at 90 nautical miles from Evansville, 111 degrees at 110 nautical miles, and 262 degrees at 125 nautical miles. The report continues by indicating that the area of precipitation is moving from 260 degrees at 30 knots. Finally, it shows that the maximum tops of the clouds are at 12,000 feet, located at 324 degrees at 39 miles. The predicted surface weather within a 5 statute mile radius from the center of an airport's runway complex is called a Terminal Aerodrome Forecast, or TAF. Each forecast is issued 4 times a day and is valid for a 24-hour period. The codes used in a TAF are similar to those used in a METAR. In this example of a terminal aerodrome forecast, you can find forecast wind, visibility if 6 statute miles or less, weather, and sky conditions. Let's take a look at a typical TAF. This forecast is for KDEN, Denver, Colorado. Following the 4-letter station identifier is the date and time of issuance. The first 2 digits are the date, immediately followed by the time in Zulu. This forecast was issued on the 9th of the month at 17:45 Zulu. The next group indicates the valid period. In this case, the forecast is valid on the 9th of the month from 1800 Zulu through 1800 Zulu on the following day. The forecast is calling for winds from 220 degrees true at 20 knots. Visibility is expected to be 2 1/2 miles with light rain showers. The ceiling is forecast to be 2,000 feet broken. When the wind direction fluctuates or the wind speed is 3 knots or less, it is encoded as VRB. Cumulonimbus, CB, is the only cloud type included in a terminal aerodrome forecast. When the weather is expected to change during the forecast period, the TAF will indicate the change at the end of the report. For example, at Denver, from 0100 Zulu, the sky conditions are forecast to be clear through the remainder of the forecast. When a possibility exists for a change in the wind, visibility, weather, or sky conditions, and those forecast changes are expected to last less than an hour, they are preceded by the term TEMPO, or tempo. This report predicts that between 0400 Zulu and 0800 Zulu, visibility will drop to 3 statute miles associated with thunderstorms and rain showers. An overcast layer of cumulonimbus clouds with bases at 3,000 feet is also expected. BECMG, or becoming, is used when a gradual change in conditions is expected and should not last more than 2 hours. The forecast time of the weather is listed by a 4-digit number representing the beginning and ending hours of the change and follows the becoming indicator. When there is a 30 to 49% chance for the occurrence of thunderstorms or precipitation, you will see a probability group. Thunderstorms or precipitation expected to be present more than 50% of the time will be included in the prevailing weather or a tempo. Here, there is a 40% chance of 3 statute miles visibility along with thunderstorm and rain showers between 0000 and 0400 Zulu. This report also predicts that a broken layer of cumulonimbus clouds with bases at 3,000 feet is expected during this 4-hour time period. Now let's look at the area forecast, or FA, which also provides valuable weather information. Each forecast predicts the general weather conditions over an area the size of several states. You can use it to help determine en route weather as well as probable weather conditions at airports without terminal aerodrome forecasts. An area forecast is divided into 4 basic sections: communications and product header, precautionary statement, synopsis, and VFR clouds and weather. The communications and products header identifies the office issuing the forecast, the date and time of issuance, the valid times for forecast weather, and the states covered by the forecast. The precautionary statements, a standard note on each area forecast, indicate that thunderstorms imply possible severe or greater turbulence, severe icing, low-level wind shear, and IFR conditions. The statement in this example, see AirMet Sierra for IFR conditions and mountain obscurations, alerts pilots that IFR conditions and/or mountain obscurations may be occurring or forecasted to occur in a portion of the forecast area. Always check the latest AirMet for your area of flight. In addition, all heights not given in terms of mean sea level are noted in the forecast by the abbreviations AGL for above ground level, or CIG for ceiling. This section of the area forecast is the synopsis, which contains a brief summary of the location and movement of fronts, pressure systems, and circulation patterns for an 18-hour period. This synopsis states that there is an upper-level trough in north-central Montana through southern Idaho that will move east into the plains by 00 Zulu with an upper-level ridge building over Washington, Oregon, and Northern California. There is also a surface high pressure over eastern Washington and northern Idaho that will build southeastward into southwest Wyoming behind the cold front. The VFR clouds and weather portion of this section is broken down by states or areas and describes the cloud conditions, weather, and/or visibility that are marginal VFR or better. In this example, Arizona is forecast to have scattered to occasionally broken clouds in the northern half of the state. The southern and far eastern portions of the state are expected to have scattered clouds with bases at 15,000 feet AGL and a chance of isolated light rain showers after 1500 Zulu. Included in the VFR clouds and weather portion is a 12-hour forecast and 6-hour categorical outlook for each state. The outlook for this area is VFR. When weather conditions warrant, the National Weather Service will issue in-flight advisories in the form of airmets, sigmets, and convective sigmets. Although classified as in-flight advisories, these reports are also included in computer printouts. These advisories notify pilots of the possibility of hazardous flying conditions, which may not have been forecast at the time of the initial briefing. An airmet describes areas of turbulence, icing, sustained surface winds greater than 30 knots, ceilings below 1,000 feet and/or surface visibility below 3 statute miles, and mountain obscuration of sufficient intensity or extent. There are 3 airmet designators. Sierra always represents areas of IFR, Tango always represents areas of turbulence, and Zulu always represents areas of icing. Here, airmet Sierra is valid for Wyoming and Colorado and indicates areas of mountain obscuration and IFR conditions. Sigmets describe non-convective weather conditions of greater intensity than those in airmets. Sigmets are issued for severe or extreme turbulence or clear air turbulence, severe icing, dust or sandstorms that lower surface or in-flight visibilities to below 3 miles, or volcanic ash. Anytime weather conditions meet or exceed these criteria, or are expected to occur within 2 hours, a sigmet will be issued. Convective sigmets report areas of severe thunderstorms, tornadoes, heavy precipitation, hail of 3/4 of an inch or greater, wind gusts to 50 knots or more, embedded thunderstorms, and lines of thunderstorms. However, since conditions of severe or greater turbulence, severe icing, and convective low-level wind shear are normally associated with thunderstorms, these conditions are assumed to exist and are not specified in the report. Convective sigmet bulletins are issued at 55 minutes past the hour and are valid for 2 hours. Appended to each convective sigmet is an outlook valid for 2 to 6 hours after the issuance time. This outlook discusses further convective development with emphasis on lines or clusters of thunderstorms and severe or embedded thunderstorms. Another element of your weather briefing is the winds and temperatures aloft forecast. This forecast helps you calculate en route speed and performance figures for your aircraft. Winds and temperatures aloft forecasts are derived from information gathered by weather balloons released at 12-hour intervals. The forecast gives the wind direction in degrees from true north, wind speed in knots, and the temperature in degrees Celsius for selected altitudes. Forecasts for specific locations are indicated by station identifiers. Each identifier is followed by code groups which show the wind direction, wind speed, and temperature at specified forecast levels. The first 2 digits represent wind direction in tens of degrees, with the next 2 digits representing the wind speed. Where appropriate, The remaining digits record the forecast temperature. In this example, the coded group forecasts a wind from 200 degrees at 6 knots. The temperature at this altitude is forecast to be 13 degrees Celsius. Due to terrain influence, wind forecast information is omitted from any level that is within 1,500 feet of the ground. Likewise, the temperature is omitted from the 3,000-foot level and any other level which is within 2,500 feet of the surface. Since temperatures are always negative above 24,000 feet, the minus sign is omitted above this level. Notices to airmen, or NOTAMs, are usually included with printed weather reports. NOTAMs alert you to recent changes in the airspace system that could affect the safety of your flight. Here, a temporary flight restriction is in effect until further notice. This restriction is due to dynamite blasting, and only authorized flights may be conducted within 500 feet over the blasting area. In this program, you have seen a brief overview of some of the major printed reports and forecasts that are available to you in preparing for any flight you take. When interpreted correctly, these reports and forecasts help you understand the weather you will encounter in flight.
In addition to the printed reports and forecasts disseminated by the National Weather Service, there are also various graphic weather products available for your use. Some of the more common graphic products are the surface analysis, weather depiction, radar summary, and low-level significant weather prognostic charts. These charts are designed to give you the general weather picture over a large geographic region in a glance. The surface analysis chart is a good source for this type of information. Here, surface pressure, frontal areas, and surface weather information have been combined into a single graphic display. Low and high pressure centers are readily identifiable by large L's and H's. Isobars, connecting points of equal pressure, are plotted around these centers. They are normally drawn at 4 millibar intervals and are labeled with the last 2 digits of the barometric pressure. Here, the isobar labeled 96 represents 996 millibars. Frontal boundaries are noted by solid lines. The direction and type of front can be determined by the symbols attached to the line. The front shown here has pointed barbs on one side, which identify it as a cold front. Since the barbs are on the east side of the line, the front is moving in an easterly direction. Weather briefers may color cold fronts blue to help you identify them. Half circles identify this as a warm front. Again, the direction of movement is shown by the placement of the symbols on the frontal line. In this case, it is moving to the north. For ease of identification, warm fronts may be colored red. A combination of half circles and barbs on opposite sides of the lines is used for a stationary front. The line is usually colored with alternating red and blue segments. A line depicting an occluded front has both symbols on the same side and is usually colored purple. In addition to pressure and frontal information, the surface analysis chart provides weather observations for a large number of reporting stations located throughout the country. For each location, a station model provides the reported weather conditions at the time the chart was produced. Let's take a closer look at each element of the model. The identifier is printed below and to the left of the symbol. LAF represents Lafayette, Indiana. The circle itself is shaded according to the amount of cloud cover that is present. Here, 3/4 of the circle is filled, indicating a broken cloud layer. A wind pointer indicates the true direction from which the wind is blowing. You can read the speed using the barbs at the end of the wind pointer. Each long barb represents 10 knots, while each short barb is 5 knots. In this example, the wind is out of the southeast at 15 knots. A pennant represents 50 knots of wind, while a circle around the station indicates a calm wind. When clouds are present, the level and type will be depicted in the station model. Low clouds are shown below the station model, with middle and high clouds printed above the symbol. You can find the decoding information for these symbols in various FAA publications and at flight service stations. To the left of the station circle is the temperature and dew point. If there is precipitation or weather obscuring the visibility, the appropriate symbol will be printed between the temperature and dew point figures. The symbol here represents intermittent snow. To the lower right of the station, the precipitation over the last 6 hours is recorded in hundredths of inches. The atmospheric pressure measured in tenths of millibars is shown in the top right corner. You must add the decimal and prefix the number with a 9 or 10, whichever brings the value closer to 1,000. The pressure at Lafayette is 1,018.7 millibars. Below this reading is the amount and tendency of any pressure change over the past 3 hours. At this station, the pressure has decreased 0.7 millibars. To ensure that you have the latest information, you should note the time of the observation. It is shown in a date-time box in the lower left portion of the chart. Then, by comparing the current surface analysis chart with earlier ones, you can get an indication of how the weather systems are progressing. Another graphic display of the weather is the weather depiction chart, which can be very useful in determining general weather conditions and the locations of low clouds and visibility. This chart, like the surface analysis chart, uses a station model to present the reported weather at various locations. However, this model has been simplified, making it easier to read. Cloud coverage is shown in the same manner, but the pressure information, wind, temperature, cloud types, and station identifier are not plotted. Below the station circle is the height of the ceiling or lowest cloud layer in hundreds of feet. This station model is showing overcast skies at 10,000 feet AGL. If the visibility is 5 statute miles or less, it is printed to the left. Weather or obstructions to visibility may also be shown. The visibility at this station is 3 miles in fog. Although pressure and wind information is not provided on these charts, areas of significant weather are outlined to help with route planning. Shaded areas indicate IFR conditions and contain ceilings less than 1,000 feet and/or visibilities less than 3 miles. Areas of marginal VFR weather with ceilings between 1 and 3,000 feet and/or visibilities between 3 and 5 miles are shown in solid lines with no shading. Finally, weather depiction charts also give the position of fronts. This frontal information, when added to the areas of IFR and marginal VFR weather, will give you a very good picture of the general weather affecting your route. The radar summary chart is another graphic display that is frequently used by pilots and briefers. It is used to identify large areas of precipitation and hazardous weather that could affect your flight. Radar summary charts are developed by using reflected radar energy or echoes of the precipitation areas. The more severe the precipitation, the stronger the echo. Each radar observation station is then combined into one hourly map. The strength of the echo returns is shown by solid lines surrounding shaded areas. The outermost line indicates precipitation that is light to moderate. A second line within the echo depicts heavy to very heavy precipitation, while a third line shows where intense to extreme precipitation exists. A solid single line shows a line of echoes with the boxed SLD indicating that the echo coverage is 0.8 or greater along the line. The direction of movement of an individual cell is indicated by an arrow. The speed, 45 knots, is shown at the point of the arrow. The letters NE indicate areas with no echoes, while the letters TRW stand for thunderstorms and rain showers. Echo tops are encoded in 2 or 3 digits. you will need to add 2 zeros to determine the actual altitude. For example, the top of this cell is at 34,000 feet, and the top of this one is 19,000 feet. Because it is assumed that all precipitation displayed on the chart reaches the surface, the chart does not include a symbol to show the base of the echoes. An area which is under a severe weather watch will be marked with a dashed box and an alphanumeric identifier. In this case, WS0006 identifies this as a severe thunderstorm watch area. When an area is marked with a WT, it is identified as a tornado watch area. When using a radar summary chart, remember that radar only detects areas of liquid or solid precipitation. It will not, for instance, show areas of fog, and the actual cloud tops may be higher or lower than the figures shown on the chart. The charts we have seen so far in this program have all depicted observed weather conditions. Other charts, including the Low-Level Significant Weather Prognostic, or PROG chart, offer a forecast of future weather. PROG charts are divided into 4 panels. The top 2 contain 12 and 24-hour forecasts of IFR and marginal VFR conditions, turbulence, and freezing levels. These 2 panels forecast the weather from the surface through approximately 24,000 feet. The bottom 2 panels forecast the location of pressure and frontal systems, as well as the areas and types of precipitation on the surface itself. Areas of IFR conditions, where ceilings are expected to be less than 1,000 feet and/or visibilities less than 3 miles, are enclosed by solid lines. Scalloped lines enclose marginal VFR areas where ceilings are expected to be 1,000 to 3,000 feet and/or visibilities are forecast to be between 3 and 5 statute miles. Areas which are forecast to have moderate or greater turbulence are enclosed by dash lines and contain symbols indicating the intensity and altitude of the turbulence. In this case, moderate turbulence can be expected from the surface to 3,000 feet over this area of the United States. The position of the freezing level at specified altitudes is also shown on the chart. A zigzag line is used to identify the freezing level at the surface. Freezing levels above mean sea level are indicated by dashed lines drawn at 4,000-foot intervals. On the lower panels, fronts and pressure centers are presented in the same manner as they are on surface analysis charts. In this example, this high has a barometric pressure of 1,022 millibars. Solid lines are used to denote areas of precipitation. Symbols are inserted to denote the type of activity expected. For example, 2 dots indicate rain, while 2 star symbols represent snow. A mixture of precipitation is indicated by showing 2 pertinent symbols separated by a slash. These symbols represent rain showers and thunderstorms. A bold dash line is used to separate precipitation with contrasting characteristics within an outlined area. For example, this dashed line separates an area of snow from an area of rain. Continuous precipitation is a dominant and widespread event, and therefore is shaded. Intermittent precipitation is a periodic and patchy event and remains unshaded. Shading is also used to denote the amount of precipitation projected in a specified region. Areas with more than half coverage are shaded, and half or less coverage unshaded. The charts that have been presented in this program are but a few of the graphic weather products that are available for your use. As we have seen, charts of these types are very useful for obtaining a brief, general overlook of the existing and forecast weather along your intended route of flight and the surrounding areas. In previous segments, you learned how to interpret printed reports and forecasts, as well as graphic weather products. But as a pilot, how does this information get into your hands? You can retrieve weather information from a wide variety of sources. Government facilities and private companies make weather reports and forecasts available by phone, television, fax, radio, and the internet. First, let's take a look at the sources of pre-flight weather information available to you. The most common source of pre-flight weather information is the Flight Service Station, or FSS. Flight service stations are FAA-operated facilities spanning the contiguous United States, as well as Alaska and Hawaii. You may encounter the term Automated Flight Service Station, or AFSS. This term is sometimes used to differentiate the current FSSs that employ advanced technology from the former non-automated FSSs. An FSS typically offers a number of services, including pre-flight weather briefings, IFR and VFR flight plan processing, assistance for aircraft that are lost or in distress, and aid for search and rescue operations. Some flight service stations also have the ability to provide in-flight weather information in the form of en route flight advisory service, or EFIS. If you happen to live in a city where an FSS is located, you can visit the station and receive pre-flight weather services in person if the briefers are able to handle your request at that time. Due to the limited number of stations in the U.S., however, a telephone briefing is a much more common means of receiving weather information. You can reach a flight service station on the ground by simply dialing a toll-free number anywhere in the U.S. When you dial 1-800-WXB-RIEF, you will be connected with the FSS nearest your location. The FSS phone system allows you to access a pre-flight weather briefer, along with other services such as FastFile, a flight plan filing tool. When you speak with a pre-flight briefer, you can request one of three types of weather briefings: an Outlook briefing, a standard briefing, and an abbreviated briefing. Before you can receive a briefing, however, you must provide some background information regarding your flight. This allows the briefer to tailor the weather information to your specific needs. An Outlook briefing is used when your departure is 6 or more hours away. This type of briefing is very useful for getting an overall picture of the general weather trends that may affect your flight. As your departure time nears, a standard briefing is necessary to obtain the most complete and in-depth weather data. A standard briefing is comprised of 12 separate and sometimes lengthy elements, so be prepared to write when you call. The briefer normally provides you with the following information: reported and forecast adverse weather conditions, information regarding whether or not VFR is recommended based on the current and forecast weather, an overall synopsis of weather systems, the current weather conditions, the en route weather forecast for your route of flight, the forecast for your destination airport, the winds and temperatures aloft forecast, NOTAMs, any air traffic control delays if applicable, a request for pilot reports, the availability of EFIS or FlightWatch, weather updates, and any other information you request, such as military activity along your flight route. Just prior to your departure, you may elect to check the weather one more time. An abbreviated briefing allows you to request one or two specific items and be advised of any changes in the weather since your last briefing. To expedite this briefing, be sure to include as much background information as possible, including the time and source of your last briefing. If you do not need to speak with a weather briefer, but you would like current weather information to aid in your pre-flight planning, some FSSs offer the Telephone Information Briefing Service System, or TIBS. You can access the TIBS recordings using the FSS 1-800 number. Typically, these recordings include route and/or area briefings for specific locations in the FSS region.
This recording prepared at 1408 Zulu. Briefing summary of current weather in eastern Colorado. valid until 1500 Zulu. Summarize current conditions. A few clouds at 9,000 to 1,000 and high scattered cirrus. Visibility is unrestricted. Winds are generally northwesterly to northeasterly.
The TIBS system is recommended for preliminary briefings only and should not replace a standard weather briefing. If you have any questions about the recorded information, you can remain on the line to access a weather briefer. Be sure to provide the briefer with any background information in order to expedite the process. Another system you can use to receive complete weather briefings is the Direct User Access Terminal Service, or DUATS. DUATS is a free service that can be accessed on the Internet or with a modem and a 1-800 number. You can obtain all the items of a standard weather briefing through DUATS, as well as selected reports for specific locations. You can also file both VFR and IFR flight plans. DUATS, however, does not provide any details on military activities. You'll need to contact a flight service station for this information. You are required to have a current medical certificate to access the DUATS system. Further information regarding the DUATS service can be found in the Aeronautical Information Manual. In addition to DUATS, a number of organizations offer weather information by phone or on the Internet. While many of these sites and services are free, some require membership or specific user fees. Just one of many Internet sites providing weather information is the National Weather Service website, which is operated by NOAA, a weather service branch of the U.S. government. While websites are excellent sources of pre-flight weather data, the information presented may not be the most up-to-date and should not be used in place of a complete weather briefing from an FSS or the DUATS system. Jeppesen also provides several weather resources for pilots, such as JetFax, a worldwide weather fax service available for a small user fee. A complete listing of Jeppesen weather products, including JetFax, can be found at jeppesen.com or at flightneeds.com. Now that you've discovered where to obtain weather information prior to flight, let's explore how you can get updated weather information while airborne. One of the best sources of en route weather is En route Flight Advisory Service, or EFIS, also known as FlightWatch. This service is available from selected flight service stations. The frequency for FlightWatch is 122.0. After giving the EFIS specialist the details concerning your flight and your request, the briefer relays the latest weather information. You can also access weather data by monitoring selected VOR and NDB stations. These facilities normally provide local weather information updates or weather advisories. One such source of en route advisories is the Hazardous In-Flight Weather Advisory Service, or HIWAS, which is continuously broadcast over selected VORs. Information available through this system includes airmets, SIGMETs, convective SIGMETs, summarized severe weather forecast alerts, center weather advisories, and urgent PIREPs. The nav aids and frequencies used for HIWAS can be found in the Airport Facility Directory. Nav aids with HIWAS capabilities are also noted on aeronautical charts.
HIWAS for Miami Center area, recorded at 1845 Greenwich. Convective SIGMET 17 Echo. Between Key West and 50 nautical miles west of Vero Beach, line of thunderstorms 25 nautical miles wide.
Other in-flight services which provide surface weather observations include the Automated Weather Observing System, or AWOS, and the Automated Surface Observing System, or ASOS. These systems record surface weather observations and automatically transmit real-time weather.
Denver Centennial Airport. Automated weather observation 2116 Zulu. Wind 040 at 12.
AWOS and ASOS broadcasts can be received up to 25 nautical miles from the station and up to a maximum altitude of 10,000 feet AGL. These stations are also accessible on the ground by phone. AWOS and ASOS facilities, frequencies, and phone numbers are listed in the Airport Facility Directory and the J-AID, as well as noted on aeronautical charts. As you have seen, there are numerous weather sources available for your use, and more methods to obtain accurate weather data continue to be developed. Additional information can be found in the FAR AIM, advisory circulars, and other sources. You should always receive a pre-flight briefing before your departure. While en route, take advantage of EFIS and other en route information services to keep abreast of changes in the forecast weather. Fly safe by staying advised of current and expected weather conditions. With the wide selection of services available, obtaining the required weather data for your flight is both quick and easy.
How far will it go? And how high will it fly? Every airplane has its own unique performance capabilities and limitations. While one can fly extremely fast, another can take off and land on very short runways. It's not only important that you realize different airplanes have distinctive capabilities, it's also essential that you understand that an airplane's performance varies considerably under different flight conditions. Altitude is a primary item affecting performance. Specifically, as you gain altitude, the atmospheric pressure decreases. With a normally aspirated engine, the less dense air reduces engine power and overall airplane performance. It's essential that you consider this when operating at high elevation airports. Air density also decreases as the temperature rises because air molecules expand as they are heated. Therefore, the performance of your airplane diminishes on hot days. Finally, if the humidity is high, the air entering the engine contains water vapor, which takes up space normally available for vaporized fuel. This moist air tends to retard even burning in the cylinders. One of the most effective ways to determine how your airplane will perform is by computing density altitude. Earlier you learned that density altitude is pressure altitude corrected for non-standard temperatures, and that they equal one another only when standard conditions exist. Now let's look at an example of how density altitude is calculated and what this value actually means. Imagine that you will be departing an airport located at sea level. If standard atmospheric conditions exist, your airplane should perform as expected for sea level operations. Let's assume that the pressure altitude is the field elevation. However, the temperature is 40 degrees Celsius, or 25 degrees above standard. By using a chart or flight computer, you'll find that at 40 degrees Celsius, the density altitude is approximately 2,800 feet. This computed density altitude value means your airplane will perform as if it were departing an airport nearly 3,000 feet higher than the one where it's actually located. Because the density of the air is so much less with this above standard temperature, your airplane's performance will diminish. It's important to remember that the higher the density altitude, the lower the airplane performance. Remember that high altitudes, high temperatures, and high humidity all equal a high density altitude. Most modern performance charts have the density altitude computations built into them. But before we look at some of these performance charts, let's consider a few other factors which influence performance. You have learned that the air moving around the wings produces lift. Likewise, existing wind conditions have a big impact on airplane operations, specifically takeoff and landing performance. For example, headwinds are desirable for both takeoffs and landings. During the takeoff roll, a headwind supplies additional lift to the wings. This enables you to lift off earlier than during a no-wind condition. During a landing, the headwind reduces your ground speed as you approach the runway. This, in turn, shortens the landing roll. Aircraft performance can also be influenced by the runway itself. Many runways slope from one end to the other. You need to consider the gradient when determining takeoff and landing distances. For example, if you land uphill, the airplane will decelerate faster than normal, which will decrease the landing roll distance. On the other hand, departing uphill will lengthen the takeoff roll since it takes longer to accelerate to liftoff speed. The opposite conditions exist when the runway slopes down. Now your takeoff roll will decrease because you're able to accelerate faster. However, your landing roll will increase because it takes longer to slow down. You should also pay close attention to the effects of operating on runways with surfaces of snow, mud, water, or grass. The friction produced by these surfaces may significantly increase your takeoff roll. Now let's turn our attention to some examples of performance charts that you'll likely encounter during your flight planning. The most important source of information available for these calculations is the pilot's operating handbook. However, the performance data from each POH applies only to a specific aircraft. Therefore, when you're determining the performance figures for a particular aircraft, make sure you're using the correct POH. Suppose you're going to be departing a short field and you want to know the ground roll and total distance required to clear a 50-foot obstacle. For this type of calculation, you'll need to refer to the takeoff distance chart. Before beginning, you need to note the conditions necessary to achieve the computed values on the chart. These include the flap setting, the power setting prior to brake release, the runway conditions, and the associated winds. Other notes are included for making adjustments for varying wind and runway conditions. For this example, let's assume the following conditions exist. The pressure altitude is 3,000 feet. The temperature is 20 degrees Celsius. And the airplane is at its maximum takeoff weight of 2,400 pounds. The table lists the appropriate airspeeds for liftoff as well as the recommended speed once you're 50 feet off the ground. These airspeeds help to assure that the airplane will perform as shown. First, locate the pressure altitude of 3,000 feet. And then move horizontally to the current temperature of 20 degrees Celsius. Under these conditions, the ground roll distance is 1,230 feet, and the distance required to clear a 50-foot obstacle is 2,295 feet. As you can see, this chart does not cover every temperature or pressure altitude possible. Therefore, it's often necessary to interpolate values between the given variables. Now let's examine a cruise performance chart for a Beechcraft Sierra. This type of chart is extremely useful for estimating the speed of your airplane, as well as the fuel consumption at various altitudes and power settings during cruising flight. For this problem, let's assume the following conditions exist. The propeller will be set to 2,400 RPMs. The airplane weighs 2,600 pounds. The pressure altitude is 2,000 feet. And the temperature is standard at this altitude. After verifying that you have the correct chart, start with the pressure altitude of 2,000 feet. Move horizontally until you reach the information for a standard day. Within this area, you'll find the manifold pressure you should use to achieve the desired results. In this case, it is 22.3 inches. The fuel flow at this power setting is 54 pounds, or 9 gallons per hour. and the true airspeed is 120 knots or 138 miles per hour. Landing distance charts are also helpful planning tools. Although they vary somewhat, they're designed to enable you to determine how much runway is required to land the airplane safely. This is particularly important if your destination airport has a relatively short runway. The layout used in this particular chart provides precise landing information as long as you follow the specified conditions. For example, this chart is only valid during a power-off landing with the flaps set at 40 degrees. While some landing charts provide just the ground roll distance, this one is designed to show the total distance required to land over a 50-foot obstacle. For this sample problem, we'll assume the following conditions exist. The temperature is 30 degrees Celsius. The pressure altitude at the airport is 4,000 feet. The airplane's landing weight is 2,100 pounds. And you're landing into a 5-knot headwind. Now use these values to predict the landing distance by following a path through the graph. The first step is to locate the current temperature of 30 degrees. Next, proceed vertically to the 4,000-foot pressure altitude of the destination airport. Move horizontally to the weight reference line. And then move diagonally to the airplane's landing weight, which is 2,100 pounds. Continue horizontally to the no-wind reference line. Then move diagonally until you reach the current headwind of 5 knots. Now move straight across to read that the landing distance over a 50-foot barrier is approximately 1,080 feet. Because your airplane's performance can vary substantially, it's vital that you understand how changing conditions can alter its usefulness. As you gain knowledge of how density, altitude, surface winds, aircraft weight, and runway conditions affect the airplane, and learn to use performance charts properly, you can safely and accurately predict the capabilities as well as the limitations of your airplane.
There are many factors that affect the ability of an airplane to perform under certain conditions. One of these is proper loading of passengers, cargo, and fuel. In this section, you'll learn how to determine if your airplane is within the weight and balance limits which have been established by the manufacturer. Each airplane is designed to be operated at or below specified maximum weights and within a certain center of gravity range. As you learned earlier in the stability section, improper loading can adversely affect performance. In addition, all figures in the performance section of the POH are based on an airplane being loaded within the specified limits. Let's begin our discussion by looking at the various aircraft weights with which you should be familiar. The starting point for any calculation is the basic empty weight, which includes the airplane, optional equipment, unusable fuel, and full operating fluids, including oil.
Payload includes the weight of the passengers and any cargo or baggage. Useful load includes the payload and the weight of the flight crew and usable fuel. The sum of the basic empty weight and the useful load is called the ramp weight, which is the weight of the aircraft during ground operations.
You adjust ramp weight by subtracting the fuel to be used for engine start, taxi, and run-up to get takeoff weight. This weight should not exceed the maximum takeoff weight found in the POH or the weight and balance records. If your airplane is too heavy, it might have trouble getting off the ground. An airplane also has a maximum landing weight. This weight can be determined by subtracting any fuel used during the flight from the takeoff weight. The maximum landing weight can also be found in the airplane's POH. If you operate your airplane above this weight, The shock absorbed during landing may overstress the landing gear or damage the wing support structure. When you have determined that your loaded airplane will not exceed the maximum weight, you need to ensure that it is safely balanced. An airplane is in balance when its center of gravity, or CG, is located within the limits prescribed by the manufacturer. The CG is measured in inches aft of a reference datum, which is an imaginary vertical line set at some point along the longitudinal axis of your airplane. The datum can be set anywhere the manufacturer chooses. Some popular locations are a point ahead of the airplane, the firewall, or the leading edge of the wing. For this airplane, it is located at the nose. The center of gravity for every component is located in relation to this point. The longitudinal distance in inches from the datum is called the arm or station. Since the baggage area for this aircraft is located 142.8 inches aft of the datum, its arm is considered to be 142.8. If you multiply the weight of an object by its arm, you get its moment. For example, the weight of the suitcase is 25 pounds. Multiplying this weight by the arm results in a moment of 3,570 pound-inches. By adding all the moments together and then dividing by the total weight, you'll get the center of gravity for the loaded airplane. It's your responsibility as a pilot to make sure this CG is within limits. To help you accomplish this task, manufacturers use three basic methods. These include the computational, graph, and table methods. Let's first work a problem using the computational or mathematical method. Your first step is to find the basic empty weight and moment in the aircraft's weight and balance records. This figure includes the weights of all permanently attached items. Therefore, if any equipment is added or removed, the weight and balance records must be adjusted. For this problem, let's assume the basic empty weight is 1,500 pounds. This weight and its moment, along with its CG if given, is then transferred to a worksheet which contains 4 columns labeled as shown. You must then complete the weights and moments for the rest of the useful load. As a sample problem, assume you weigh 170 pounds and you're going to be carrying 2 passengers who each weigh 180 pounds. Since one of the passengers will be sitting in the co-pilot seat, you need to add your weight to that of the passenger. The result is 350 pounds. Since the arm for the pilot and front seat passenger is 80.5 inches aft of datum, the moment is 28,175 pound-inches. The moment for the rear seat passenger is 21,258 pound-inches. The next major item is fuel. Since you intend to carry the maximum amount of usable fuel, which is 48 gallons, and since each gallon of avgas weighs 6 pounds, the total fuel load weighs 288 pounds. This weight times the arm of 95 inches yields a moment of 27,360 pound-inches. The last item is the baggage, which in this problem weighs 60 pounds. Its moment is 8,568. If no more items are loaded on the airplane, the computational list is complete. Your next step is to add the weight and moment columns. In this example, the total weight of the loaded airplane is 2,378 pounds. And the moment is 214,211. You should then verify that the total weight is less than the maximum weight found in the POH or the weight and balance records. If not, you will have to make a choice of not carrying as much fuel, taking less baggage, or leaving some of the passengers behind. You can now determine the center of gravity for your airplane by dividing the total moment by the total weight. The CG with this loading is located 90.1 inches aft of the datum. To determine if the CG is within limits, refer to the airplane center of gravity limits graph. In this example, the numbers on the right represent the airplane's weight, and the numbers on the top represent the CG location. Enter the graph on the right at the number that matches the total weight of the airplane, which in this case is 2,378 pounds. Then move to a point just right of the 90-inch aft CG location. Since this point falls within the approved CG envelope, your airplane is properly loaded. Some aircraft manufacturers use the graph method, which is a simplification of the computational method. It allows you to determine the moment of each item without having to multiply each weight by its arm. In this example, assume this airplane is carrying the same load as before. To find the moment for yourself and your front passenger, enter the graph from the left side at 350 pounds. Proceed horizontally to the pilot and front passenger line. Then drop straight down and read the moment divided by 1,000. In this case, it is 13.0. Enter this moment in the appropriate space in the worksheet. Then follow the same procedure to find the moments for the remaining items. Once you have all the items listed and totaled, you must compare the total moment with the total weight to determine if your airplane is within limits. Notice that with this type of graph, you don't have to do any calculations to determine the center of gravity. Another simplified method of determining moment is the table method. It requires only that you locate a given weight, then find the corresponding moment. Notice that the moments in this table must be multiplied by 100 to compensate for the reduction factor. Also, if a single weight exceeds the limit, you should use two lower weights which, when added together, equal the single weight. For example, you know that you and the front passenger weigh 350 pounds. Since the table only goes to 200 pounds, you'll need to find the moment for yourself and then add it to the moment for the front passenger. You then need to transfer the weights and moments to the weight and balance worksheet. Once you've finished totaling the weights and moments, you can use the moment limits versus weight table to determine if you're within limits. Here, you must find your loaded weight and then verify that the total moment is within the minimum and maximum limits. Weight and balance is a factor that should be considered on every flight. Taking the time to verify that your airplane is properly loaded will increase performance and help ensure that you have a safe flight.
In this program, we'll look at how to solve navigational problems using two different types of flight computers. First, we'll discuss the mechanical slide graphic, or CSG computer. Then we'll cover the TechStar, which is an electronic flight computer. Because this program is only an introduction, you should study the operator's manual for the computer you've selected in order to become thoroughly familiar with it. If you have a computer handy, you might want to work the problems as we're going through the program. We'll pause periodically to allow you to complete the problem. If you're only interested in the TechStar computer, you can forward the tape to that part of the program. The CSG computer has two sides, the wind side and the calculator side, which can be used to solve a variety of problems including time, speed, distance, fuel consumption, true airspeed, density altitude, and conversions. There are 3 scales on this side of the computer. The outer, or A scale, can represent distance, fuel, speed, or other units, depending on the problem you're solving. The middle, or B scale, may represent similar items, as well as time in minutes. The inner, or C scale, is simply a conversion of time in minutes to time in hours and minutes. The outer scale is fixed, while the inner 2 scales are printed on a single rotating disc. The numbers on the computer can be assigned different values depending on the problem. For example, the 60 can have a value of 0.6, 6, 60, 600, and so forth. By mentally estimating the approximate answer, you can place the decimal point in the proper position. The graduations between the numbers, however, are not always equal. For example, between the 80 and 90, there are 10 divisions, with each division representing 1 unit. The third line right of 80 could be 8.3, 83, or even 830. Between the 21 and 22, there are only 5 divisions. Here, each line represents 2 units, so the third line right of 21 could be 21.6, 216, and so forth. Most of the calculations on the computer are ratios or fractions. For example, when determining time, speed, distance problems, there are 3 variables: elapsed time, speed, which is usually ground speed, and distance. If you know any 2 of the variables, you can quickly solve for the third. The face of the computer shows you how to solve for the unknown value in these ratio problems. If your aircraft speed appears over the index, you will find distance on the A scale and time on the B and C scales. For example, assume you're planning to fly your airplane at 140 knots for a distance of 350 nautical miles. How long will your flight take? First, place the speed index under 14, which is 140 knots, when you mentally delete the 0. Then look under the 35, or the distance of 350 nautical miles, to find the time in minutes. In this case, it is 150 minutes. Notice that you have to add a 0 to the 15. 150 minutes can be quickly converted to 2 hours 30 minutes by referring to the C, or hour scale. You can also use the computer to find the distance flown in a given period of time. For instance, at a ground speed of 120 knots, how far will you travel in 2.5 hours? First, set the speed index under the ground speed of 120 knots. Then go to the C scale and locate 2.5 hours or 150 minutes on the B scale. Directly above this number on the distance scale is your answer, 300 nautical miles. You determine the ground speed of your aircraft in a similar manner. If you've traveled 349 miles in 2 hours and 15 minutes, what is your ground speed? First, locate the time for this flight. Since 2 hours and 15 minutes is not marked on the C scale, you should use the time in minutes, 135 on the B scale. For 349 miles, you'll have to estimate the distance from the line representing 345 and the one showing 350. Then you can read your ground speed directly above the speed index mark. In this case, it is 2.5 lines right of the 15. By placing the decimal in the correct position, you can determine the ground speed to be 155 knots. Fuel consumption problems are basically the same type of calculations, except that the index now points to the fuel rate, which in this case is gallons per hour. The outer scale shows the amount of fuel burned, while the inner scales still show time. Suppose in your flight planning you need to know how much fuel you will need if your destination is 3 hours away and your airplane burns 8 gallons of fuel per hour. Like the speed problem, set the index mark under the rate of 8 gallons per hour. Then find 3 hours on the inner scale, or 180 minutes on the middle scale. Read the fuel required, 24 gallons, directly above this time. Another type of fuel problem is to determine your endurance, or how much time you can stay aloft. Assume your airplane has 42 gallons of fuel on board, and it uses 11 gallons of fuel per hour. This time, set the index under 11, which is the rate per hour. Under the 42, read 229 minutes, or 3 hours 49 minutes on the inner scale. You can also use this side of the computer to determine true airspeed. However, to do this, you must know 3 things: calibrated airspeed, pressure altitude, and air temperature. While in the air, you can determine the temperature by referring to your outside air temperature gauge. For pre-flight planning purposes, you can get the forecast temperature for your planned altitude from the winds and temperatures aloft forecast. If you're unsure of the pressure altitude and you're in an airplane, you can determine it by setting the altimeter to 29.92 and reading the indication. Make sure you reset the altimeter back to the current reported setting when you're finished. Calibrated airspeed can be found by referring to the pilot's operating handbook. Once you've determined all the necessary variables, use the window marked for true airspeed and density altitude and align the temperature in degrees Celsius over the pressure altitude. Then read the true airspeed on the A scale opposite the calibrated airspeed on the B scale. As a sample problem, suppose the pressure altitude is 5,000 feet, the temperature is 20 degrees Celsius, and your calibrated airspeed is 150 knots. Using the proper window, align +20 opposite the 5. Notice that the altitude scale is in thousands of feet and plus temperatures are to the left of 0. Next, find the calibrated airspeed of 150 knots on the B scale. Then read the true airspeed of 166 knots on the A scale. Density altitude can then be read directly from the center window. If the conditions remain the same as in the previous problem, the density altitude will be approximately 6,700 feet. The other window is used to compute true altitude. Instructions are listed near the window. The computer can also be used for conversions. For example, a temperature conversion scale is located at the bottom of the disk. For nautical statute mile conversions, 2 arrows at the top of the fixed scale give the proper relationship. These and many other conversions are covered in your owner's manual. The wind side of the computer is used to determine how the wind is affecting your airplane's ground track and speed. As you learned earlier, the moment an object becomes airborne, it is affected by the wind. If the object has no propulsion of its own, such as this balloon, it will float at the same speed and in the same direction as the wind. An airplane is also influenced by the wind. While it doesn't drift freely like the balloon, it is deflected from its intended flight path and its ground speed is affected. To illustrate, suppose a free balloon is released in a 15-knot west wind. At the same time, an airplane begins a flight due north at 100 knots. After 1 hour, the balloon will have drifted 15 nautical miles to the east. The airplane, flying northward, also will have drifted this same distance. In this situation, you should have pointed the nose of the aircraft to the west of the destination to compensate for the wind drift. The angle formed between your heading and the flight path is called the wind correction angle. The wind side of the computer helps you determine to what extent you'll have to fly into the wind. There are 2 parts to this side of the computer: a rotating azimuth and a sliding grid. Notice that the grid is printed on both sides. The high-speed side is used mainly for solving problems at jet speeds. There is also a statute and nautical mile scale, which can be used on sectional and WAC charts. The low-speed side of the scale is used for aircraft flying at lower speeds. It contains concentric arcs, which represent speed and straight lines radiating from a central point, which represent degrees right or left of the center line. The rotating azimuth is graduated into 360 degrees. The center of the azimuth is a frosted transparent material, which can be marked on with a pencil. Directly in the center is a round circle known as the grommet. At the top, on the fixed portion of the computer, is a true index, which is used as a reference for plotting wind and course direction. The center line printed on the grid can represent any direction by just rotating the azimuth so the desired degrees are aligned under the index. At the top of the grid are easy-to-follow instructions on how to find ground speed and true heading. To determine how wind affects your airplane, you will need to know true airspeed, wind direction and speed, and true course, which is your intended flight path as measured from the true North Pole. The method for determining true course will be explained in the next section. Suppose that you've determined your true course to be 310 degrees. The predicted wind at your altitude is forecast to be counting the number of degrees the wind dot is located from the center line. In this case, each line represents 2 degrees, so the wind correction angle is 6 degrees left. Since the correction is to the left, you must subtract 6 degrees from the true course to obtain your true heading of 304 degrees. To verify that these figures are correct, you can visualize that the grommet represents your airplane and it's heading toward the index mark. Since the wind is behind and to your left, ground speed should be higher than true airspeed, and the true heading should be left of the true course. This concludes the coverage of the CSG computer. If you wish to learn how to operate a Techstar computer, let the tape continue. Otherwise, please forward to the next section on pilotage and dead reckoning. The Techstar electronic navigation computer is quick, accurate, simple to operate, and is designed to solve today's navigational problems. Like the different sides of a mechanical computer, the Techstar has various modes which you must use, depending on the type of problem you're solving. The time, speed, distance mode is used for determining, among other things, how far you can go, how long it will take to get there, and how much fuel you will need. The altitude airspeed mode can be used to determine density, altitude, and true airspeed. The wind mode is used to find your heading and ground speed. The weight and balance mode is used for determining gross weight, center of gravity, weight shifts, and percent of mean aerodynamic chord. The timer mode helps you compute departure, en route, and arrival times, convert different time formats, and acts as a time up or time down counter. To access the different modes, after you've turned on the computer, simply press the mode key. This displays the 5 areas. To go into any one of the modes, press the line parameter key. Let's begin with a time, speed, distance, or TSD problem. Once you're in a mode, the Techstar computer indicates which mode you're in and displays the variables you'll need to solve a problem. Notice that on this menu, the variables needed to solve a fuel problem are also displayed. Most of the calculations done on the computer are ratios or fractions. For example, when calculating time, speed, or distance, there are three variables: elapsed time, speed, which is usually ground speed, and distance. If you know any two of the variables, you can quickly solve for the third. Suppose in your pre-flight planning, you want to find out how long it will take to fly 350 nautical miles if your airplane averages 140 knots. The first thing you must do is tell the computer which variable To find the fuel rate per hour, press the compute key. The answer is 9 gallons per hour. Now let's go back to the screen where we solved for ground speed and see how this same problem can be solved using the secondary compute function. To determine fuel rate from this point, simply press the compute key a second time. This gets you to an extended output screen where additional parameters may be computed from the same variables. Then key in 21, which was the total fuel used, and transfer it to the fuel parameter line. Fuel flow can be determined by pressing the compute key again and then the flow parameter line key. The answer is the same, 9 gallons per hour. Use of the secondary compute function is further explained in the operator's manual. To determine true airspeed and density altitude, you must be in the altitude airspeed mode, which is indicated by an ALT-AS in the display. To determine true airspeed, you must know three things: calibrated airspeed, pressure altitude, and air temperature. Calibrated airspeed, which is indicated airspeed corrected for installation and instrument errors, can be found by referring to the airspeed calibration table in the pilot's operating handbook. While in the air, you can determine air temperature from the outside air temperature gauge. For pre-flight planning purposes, you can get the forecast temperature for your planned flight altitude from the winds and temperatures aloft forecast. The pressure altitude can be found, if you're in the airplane, by setting the altimeter to 29.92. However, when you've finished reading the indication, make sure you reset the altimeter back to the current reported setting. As a sample problem, let's determine true airspeed, or TAS. Assume the pressure altitude is 5,000 feet, the calibrated airspeed is 150 knots, and the temperature, which was determined from a winds and temperatures aloft forecast, is 20 degrees Celsius. First enter 5,000 feet into the pressure altitude parameter line, labeled PA. Next, enter the calibrated airspeed and the temperature. Since the temperature was determined from a forecast, we need to input the temperature into the true temperature parameter line. Had we obtained the temperature while in flight from the outside temperature gauge, this value would have been entered in the indicated temperature line. Notice that once you've entered a value into one of the OR variables, meaning the value can go into either line, dashes appear in the line next to the other variable. Now press the compute key. The true airspeed, in this example, is 166 knots. Density altitude is also determined in this mode. If the conditions remain the same as they were in the last example, all you have to do is press the compute key a second time. The answer is 6,712 feet. The wind mode of the computer is entered by pressing the wind key. When you're in this mode, the word wind will appear at the top of the display. When an object leaves the ground, it is affected by the wind. If an object has no propulsion of its own, such as this balloon, it will drift in the same direction and at the same speed as the wind. An airplane is also influenced by the wind. While it doesn't drift freely like the balloon, it is deflected from its intended flight path and its ground speed is affected. To illustrate, suppose a free balloon is released in a 15-knot west wind. At the same time, an airplane begins a flight due north at 100 knots. After 1 hour, the balloon will have drifted 15 nautical miles to the east. The airplane, flying northward, will also have drifted this same amount. In this situation, you should have pointed the nose of the aircraft to the west of the destination to compensate for the wind drift. The angle formed between your heading and the flight path is called the wind correction angle. To determine how the wind is affecting your airplane, you need to know 3 items: true airspeed, wind direction and speed, and true course. True course is your intended flight path as measured from the true North Pole. How this course is determined will be covered in pilotage and dead reckoning. Suppose you've determined your true course is 310 degrees and the predicted wind at your proposed altitude is out of the south, or 180 degrees, at 16 knots. Your true airspeed is 120 knots. What heading must you maintain to fly your desired ground track? And what effect will the wind have on your ground speed? After verifying that you're in the wind mode, press the parameter line key representing the variable you want to solve for. In this case, it's heading. Now enter the true airspeed of 120 knots into the true airspeed parameter line. Next, enter the wind direction of 180 degrees into the wind direction parameter line, labeled WDR. The wind speed of 16 knots is entered next by keying in 16 and pressing the WSP line parameter key. The true course of 310 degrees can then be entered into the course, or CRS, parameter line. Your true heading is determined by pressing the compute key. In this case, you must fly 6 degrees left or 304 degrees, to maintain a ground track of 310 degrees. Notice your ground speed, or estimated speed over the ground, is also given. In this case, it is 130 knots. If you want to find the precise speed, just press the recall key labeled RCL and the ground speed parameter line key. The precise ground speed then appears in the scratch pad. In this case, it's 129.657 knots. To verify that the wind correction and ground speed figures are correct, you might want to visualize the airplane flying on a true course of 310 degrees with the wind coming out of the south. Since the wind is behind and to the left of the airplane, ground speed should be higher than true airspeed, and the true heading should be left of the course. Now let's do a sample weight and balance problem where we solve for center of gravity. In this problem, the basic empty weight of the aircraft is 1,467 pounds, and its moment is 57,300 pound-inches. The total weight of the pilot and front seat passenger is 340 pounds, and the front seats are located 37 inches aft of the datum. The combined weight of the rear seat passengers is 280 pounds. The rear seat is located at station 73. There are 40 gallons of fuel on board. The tanks have an arm of 48 inches. There is also 20 pounds of luggage located 95 inches aft of the datum. To solve this problem using the TechStar, just follow the prompts. Input the weight and moment or arm for the first set of figures, which for this problem is the basic empty weight. Notice that when you entered the moment, dashes appeared in the arm line. The RF parameter line can be used if you wish to use a reduction factor. After you've entered the information for the first item, you'll need to press the Next key. This brings up the menu for the second set of values, which is the weight of the front seat occupants. When you press the Next key after entering an arm value, the moment appears for approximately 3 seconds before the screen goes to the next set of values. Continue entering the information for the rear seat passengers. In this example, the total weight is 2,347 pounds. The total moment is 103,740, and the center of gravity is 44.2. Now that you've worked individual problems on the TechStar, let's work a multi-part problem similar to one you might find in your pre-flight planning for a cross-country flight. You've determined you're going to be flying at a pressure altitude of 3,500 feet, and the temperature at the proposed altitude is 68 degrees Fahrenheit. Your airplane cruises at a calibrated airspeed of 120 knots, and the wind at altitude is predicted to be 095 degrees at 16 knots. The true course to your destination is 032 degrees. And the distance is 320 nautical miles. For fuel planning purposes, your airplane uses 9 gallons of fuel per hour. What you need to determine is the true airspeed, which will then allow you to find your heading and ground speed. Once ground speed is determined, you'll be able to calculate the time en route to your destination and the amount of fuel needed for the trip. The first item you must determine is true airspeed. You do this by entering the altitude airspeed mode, identifying what you are solving for, and then keying in the pressure altitude and entering it into the pressure altitude parameter line. Next, enter the temperature. Since this value must be in degrees Celsius, you must convert 68 degrees Fahrenheit to degrees Celsius. You can do this by pressing the weather conversion key. Then transfer the value in the scratch pad to the degrees Fahrenheit parameter line and compute for degrees Celsius. The result is 20 degrees. In order to transfer this to the original problem, you must press the recall key, then the degrees Celsius parameter line key. This moves the converted temperature down to the scratch pad. Now you can move this value to the original problem by pressing the mode key and the temperature parameter line key. The calibrated airspeed is the last item to enter in this mode. Now press the compute key. In this case, true airspeed is 129 knots. Since you'll need the true airspeed value to determine heading and ground speed, you must transfer this number to the wind mode. Notice that when you move the true airspeed to the scratch pad, the exact value of the true airspeed is displayed. To access the wind mode, press the mode key followed by the wind parameter line key. Once you're in the wind mode, indicate what you want to solve for. In this problem, it's heading. Then transfer the true airspeed value to the true airspeed parameter line. Next, key in the wind direction, wind speed, and true course. You're now ready to determine your heading by pressing the compute key. Since your course is 032 degrees, you must fly 6 degrees right, or 038 degrees to track the desired course. Also notice that your estimated ground speed is 121 knots. Which is 4.5 gallons. Adding this figure to the fuel en route, which you can retrieve by pressing the recall key and the appropriate arithmetic key, means you must have a little over 28 gallons of fuel on board the airplane before you make the trip. Using the Techstar computer will enable you to solve navigational problems encountered by a pilot. By becoming thoroughly familiar with it, your workload during pre-flight planning and in-flight computations will be greatly reduced.
When you leave your local area and fly cross-country, you have a choice of using one of several forms of navigation. In this program, we'll look at two of these, pilotage and dead reckoning. When you use pilotage to fly a predetermined course, you'll identify features on the ground by comparing them to symbols on an aeronautical chart. The recommended chart to use for cross-country flights is a sectional, since it provides more detail than other types of charts. Always use a current chart for flight planning and navigation. An out-of-date chart may give you incorrect information. The altitude you select is also important when you need to identify landmarks. If you're too high, detail is lost, and some checkpoints may appear too small to be positively identified. Flying too low not only gives you a poor perspective, but may restrict your visibility, especially when haze and smoke are present. The key to pilotage is selecting reference points along your route that are easy to identify from the air. Let's look at some examples. Lines that intersect or that form unusual angles are good checkpoints. Here, the jog in the road just before the intersection makes it easier to identify from the air. When you identify a checkpoint, use more than one feature. Here, the town of Windsor can be identified by the angles formed by the road and railroads to the east. In addition, there's a lake to the north and a tower to the south. When you combine all of these items, your identification of the checkpoint becomes much easier than if only one feature is used. As you gain experience, maintaining orientation by reference to landmarks will become second nature. Taking the time to adequately plan your flight will help you maintain orientation over unfamiliar or featureless terrain. When you combine your pilotage skills with dead reckoning, you have a very precise form of navigation. As with pilotage, preparation for dead reckoning navigation begins prior to flight, when you use time, speed, distance, and direction to predict the movement of your aircraft along the planned route. Thorough pre-flight planning is the key to a successful cross-country flight. You'll usually begin with an analysis of the route. In this step, you'll determine the true course, measure the distance, and select prominent checkpoints. To find the true course, you'll use a navigation plotter similar to this one. It has three basic components: a straight edge to draw the course line, a protractor to determine the direction of the course, and mileage scales to measure distance. To help demonstrate the use of the plotter, we'll use this simplified rendition of a sectional chart. The departure airport in this example is McGee, and the destination is Waynesboro. The straight edge portion of the plotter is used to draw a line connecting the two airports. This is what's referred to as a direct route. To measure the true course, select the line of longitude that's close to the midpoint of the route. Then align the straight edge with your route and place the small hole over the longitude line. Read the true course where the line of longitude crosses the protractor. Use the scale with the arrow pointing in your direction of travel. In this example, the true course is 102 degrees. The outer scale on the protractor represents easterly courses, and the inner scale represents westerly courses. If your course does not cross a line of longitude, you can use a line of latitude for the measurement. The small north-south scales are used instead of the larger east-west scales. In this example, the true course is 30 degrees. Another function of the plotter is to measure distances. Most VFR plotters have mileage scales that match WAC charts, as well as sectional charts. This plotter also has a scale to be used on terminal area charts. Always use the scale appropriate to the chart you're using. Both nautical and statute mile distances can be determined with the plotter. Let's look at how to measure the mileage for the sample flight. To measure the distance from McGee to Waynesboro, place the zero end of the plotter over the departure airport and align the straight edge with the course line. In this example, the nautical mile scale is used. The distance to the destination airport is 60 nautical miles. Now that the course is plotted and measured, return to the actual chart and select checkpoints that will help you identify the course during the flight. The number of checkpoints you select depends on the length and complexity of the flight, as well as the terrain you're flying over. Each checkpoint should be clearly marked on the sectional chart and entered on a navigation log. This log is an excellent tool for organizing all of the data about the flight. The information recorded so far includes the checkpoints, the route, which in this case is direct, the total distance, and the true course. The analysis of the route should also include measuring the distances between each checkpoint. The next planning step is to analyze the effects of wind. Here you need to determine the wind speed and direction and the true air speed. With this information you can find true heading and ground speed. You can obtain the wind information during your normal pre-flight weather briefing with the flight service station.
Wind and temperature at 3,000 are forecast to be 240 at 16 and temperature 23. At 6,000, 230 at 20, temperature 17.
The analysis of the winds aloft will usually reveal the most favorable cruising altitude. The altitude you choose should comply with the VFR cruising altitude specified in the FARs. The altitude is also important for determining the true airspeed for the flight. This airspeed may be found in the pilot's operating handbook or by using the flight computer. With the wind, true airspeed, and true course known, you can use the flight computer to find true heading and ground speed. To compute these values, you'll use the same procedures as described in the program on flight computers. To conclude the direction calculations, convert your true values to magnetic by adjusting for variation and deviation. Lines of variation are printed on sectional charts and are labeled in degrees west or east. When you apply variation to the true heading, westerly values are added and easterly values are subtracted. This line represents 2 degrees easterly variation. Therefore, you will subtract it from the true heading of 107 degrees to get a magnetic heading of 105 degrees. A good memory aid on whether to add or subtract variations is east is least and west is best. Now you are ready to adjust the magnetic heading for deviation by compensating for the instrument and installation errors in the magnetic compass. This card tells you what heading you should steer for a particular magnetic heading. The magnetic heading for this flight, 105 degrees, falls between east and 120 degrees. Since neither of these headings require a correction, the compass heading will be the same as the magnetic heading. As a final step in the route planning, compute the time and fuel requirements for the flight. These are basic time, speed, and distance calculations to find the estimated time en route, ETE, between checkpoints and the total estimated time for the complete trip. The fuel requirement should also include the reserve required by the regulations. Spaces are provided on the navigation log to record pertinent information about departure and destination airports. The sources of this information will be covered in the next program. A flight plan form is also included on the reverse side of the navigation log. This form contains spaces for you to list pertinent information about your flight. When you have completed the form, you should file the flight plan by calling the nearest flight service station.
I'd like to file a VFR flight plan.
Go ahead.
The aircraft is 52241, a Cessna 172/uniform. True airspeed 112 knots. Departure point is McGee. Proposed departure time
1600 Zulu, altitude 3,500, route is McGee, direct Waynesboro, destination Waynesboro, ETE 31 minutes, fuel on board 3 hours 40 minutes, and the pilot's name is Fred Adams, 1114 Fox.
If you anticipate a delay in your departure in excess of 1 hour, let the flight service station know. If you do not, the flight plan is considered void after an hour, and you must refile. One of the most satisfying aspects of learning to fly comes from completing a well-planned cross-country flight. As you gain experience, you will find that the fundamentals learned during pilotage and dead reckoning can be applied to most other forms of navigation.
As you saw in the last volume, basic navigation involves using visual checkpoints and time, speed, and distance calculations. In this volume, you will be introduced to other forms of navigation that use aircraft radios and ground transmitting stations. The first form of radio navigation we'll look at is the VHF omnidirectional range, which is commonly referred to as VOR navigation. A VOR station continuously sends out signals that are received by a radio in your airplane. The station is shown on an aeronautical chart by a compass rose surrounding its location. The compass rose is a graphic depiction of the signals transmitted from the VOR. These signals, called radials, extend out from the station and are numbered clockwise from magnetic north. Although the number of radials is infinite, only 360 are used. Their directions are indicated by numbers on the outside of the compass rose. Your position in relation to the VOR is usually expressed in terms of the radial on which you're located. Here, for example, the airplane is on the 090-degree radial. To receive the signals transmitted by a VOR station, you need certain airborne equipment. The antenna picks up the signal and relays it to the VOR receiver. Here it is interpreted and then sent to the VOR indicator, where the signal is displayed as navigation information. This visual display has three components. They are the course selector, the course deviation indicator, and the to from indicator. The course selector, also known as the Omni Bearing Selector, or OBS, allows you to set the desired course. The numbers and tick marks on the VOR indicator ring correspond with the numbers on the compass rose of a sectional chart. The course deviation indicator, known as the CDI, helps you determine your position relative to the course. If the needle is centered, your airplane is located on a radial. If the VOR indicator is set properly, the to from indicator tells you whether your selected course will take you to or from the VOR. When you see an off or nav indication, one of two situations has occurred. Either the signal is too weak to use for navigation, or you have just passed over the station. Now that you have a basic understanding of the VOR components, let's look at how to put them to practical use. The first step is to select and tune in an appropriate facility. Station information is represented on an aeronautical chart by a box located near the compass rose. This box includes the name of the VOR, the three-letter identifier, the Morse code identification, and the station frequency. To use it for navigation, your first step is to enter the frequency into the airplane's receiver. Turn the frequency selector knob until 117.5 appears in the display window. On this receiver, the frequency is set in the standby window, then transferred to the use window. Always verify that you have tuned in the correct frequency and that the station is in service by listening to the Morse code or voice identifier. With the station tuned and identified, it is easy to determine your position. Simply turn the OBS knob until you get a from indication. Remember, radials go out from the station. Continue turning the knob until the CDI centers. The number under the index is the radial on which you're located. Keep in mind that this display tells you where you are in relation to the station and not to the heading of the airplane. Here, for example, the airplane is located on the 070 radial from the station. The airplane could be pointing in any direction, and the VOR indicator would still read the same. However, the heading in relation to the VOR indicator does play an important role when you want to fly toward or away from the station on a specific radio. To fly away from the station on the 070 radial, all you have to do is turn the airplane until the heading indicator and radial under the index are in agreement. With a from indication and the needle centered, you'll fly away from the station on the selected radial. If you want to fly toward the station, rotate the OBS until you have a to indication. When the needle centers, note the number under the index. This is the magnetic heading to the station. Now turn the airplane until the heading indicator and radial under the index are in agreement. With the needle centered and a to indication, you'll fly toward the VOR. It's important to remember that when the VOR and heading indicators are in agreement, a to indication will take you toward the station, while a from indication will take you away from the station. This assumes that there is no wind to drift you off course. The CDI is the component on the VOR indicator that provides wind correction information. If you drift off course, the CDI will point in the direction of your desired course. A good way to visualize your position is to picture the airplane at the bottom of the VOR indicator. If the needle is to the left of the airplane, your course is to the left, and you need to make a heading correction to the left to get back on course. If the CDI moves right of center, your desired course is to the right, and you need to make a heading correction to the right. The dots along the bottom of the VOR indicator show you how far you are off course. Each dot represents 2 degrees. In this case, you're 8 degrees left of course. You need to change your heading to the right to get back on course. The amount of correction you need will depend on the strength and direction of the wind, as well as your distance from the station. In this case, a 20-degree correction angle is used to regain the course. As you near the desired course, the CDI will begin to center. When you're back on course, you'll need to turn to a heading that compensates for the wind. A good technique is to use half the original correction angle you used to regain the course. In this example, you would use a 10-degree wind correction angle. If the correction angle is too great, the airplane will drift upwind. If you are close to the desired course, simply turn to parallel the radial and let the wind drift you back. A correction angle may be required if you are farther from the course. Once you're back on the radial, apply half the original wind correction angle, which in this case is 5 degrees. There are occasions when you want to track to or from a station on a different radial than the one you're following. This requires you to leave one radial and intercept another. To help explain the intercept procedure, let's assume you're tracking outbound on the 070 radial and you want to be on the 090 radial. You should first visualize where you are and where you want to go. It's a good idea to turn to parallel the new course before you make your intercept correction. This helps to ensure your intercept is in the correct direction. Now, rotate the OBS to enter the desired course in the course selector. To intercept the 090 radial, you'll need to turn right. Continue to fly the heading until the CDI centers. When you have intercepted the new radial, turn to a heading that will allow you to remain on course with the needle centered. The intercept angle you choose depends on a number of factors. If you're flying toward the VOR at a point far from the station, a fairly large intercept angle might be required. When you're close to the station, a shallow angle can be used. If you use a small intercept angle when flying outbound, it may take a long time to reach the new radio. Since the radios diverge away from the station, a larger intercept angle may be necessary. Although VOR navigation is quite simple, you should be aware of a few unique factors, such as reverse sensing. This happens when you select and fly on a radial that is 180 degrees from your heading. When this occurs, the information provided by the VOR is opposite the normal indications. For example, to track to a station on the 070-degree radial, you need to set 250 in the course selector, then fly a heading of 250 degrees. If you mistakenly set 070 in your course selector, then fly inbound on a heading of 250, you will experience reverse sensing. If you drift to the left of course, the CDI gives a false indication that your desired course is to the left. Based on the instrument indication, a correction in the direction of the needle causes you to drift farther off course. You can avoid the problem of reverse sensing by keeping the course selector in general agreement with your heading indicator. Another unique characteristic that you may experience is a CDI fluctuation. Certain propeller RPM settings can cause the CDI to fluctuate as much as 6 degrees. You can eliminate the problem by varying the RPM slightly. Let's take a look now at how to use the VOR to determine your exact position. You've just seen how to locate where you are in relation to the station. While this procedure allows you to determine your direction from the station, it does not tell you how far you are from the station. Assuming you are on the 300-degree radial from this VOR, let's use a second VOR to pinpoint your position. First, tune and identify a second station. Next, turn the omni-bearing selector until you get a from indication and the needle centers. The course under the index, 240 degrees, is the radial on which you are located. Plot the radials from both VORs on your sectional chart. The point where the two lines intersect is your exact position. Becoming familiar with radio navigation will enhance your basic navigation skills. The information provided by VOR serves not only as a backup to pilotage and dead reckoning, but also provides accuracy in determining course, distance, and position. In the next section, you will be introduced to the Automatic Direction Finder, commonly known as ADF. When using this navigation aid, you will be able to apply some of the techniques you learned in this section.
In the last section, we looked at how to navigate using VOR. In this section, you will be introduced to the Automatic Direction Finder, which is referred to as ADF. Several ground facilities transmit signals that can be received by your airborne ADF equipment. The most common facility is called a non-directional radio beacon, or NDB. Certain commercial broadcast stations can also be received, but they should not be used as your primary source of navigation. NDB signals are transmitted in the low to medium frequency range and travel as ground waves and sky waves. Ground waves are capable of following the curvature of the Earth, while sky waves bounce off the ionosphere and can be received over great distances and at low altitudes. These signals are picked up by the ADF antenna on your airplane and relayed to the ADF receiver. This receiver has an on-off volume control knob, a station frequency selector, and several mode selectors. These selectors allow you to perform a number of functions. For example, the mode selector labeled ADF allows you to operate in either ADF or ANT, which stands for the antenna function. This mode provides maximum sensitivity to radio signals for tuning and identifying the station. With the selector in this mode, enter the NDB frequency in the receiver. You can find station information next to the NDB symbol on an aeronautical chart. The station name, frequency, and Morse code identifier are provided in a magenta-colored box similar to a VOR information box. With the station positively identified, place the selector in ADF. This allows the receiver to relay the information to the indicator, which displays it on either a movable or fixed card. Let's look at how to interpret the fixed card indicator. The needle on the bearing indicator will move in the direction of the station and stop when a strong signal is found. The pointer of the needle indicates the bearing to the station. In this case, it's 060. The tail of the needle indicates the bearing from the station. In this example, it's 240. 0 degrees on a fixed card is always aligned with the nose or longitudinal axis of the airplane. The needle indicates the number of degrees from the nose to the station. This angle is called the relative bearing. In this example, the relative bearing is 060. If your airplane is on a magnetic heading of north, you simply need to turn to a heading of 060 degrees to fly to the station. At the completion of the turn, the ADF will be pointing towards 0, indicating the station is directly ahead. If you're flying a magnetic heading other than north, you must add your magnetic heading to the relative bearing to find the magnetic bearing which will take you to the station. For example, let's assume your magnetic heading is 090 and your relative bearing is 060. When you add these two together, you get a magnetic bearing to the station of 150 degrees. To fly to the station, in this case, you simply turn to a heading of 150 degrees. When the turn is complete, the needle on the bearing indicator will point to 0 degrees. If you keep the needle pointed to 0, you are homing to the station. In a no-wind situation, you will fly directly to the NDB. In a crosswind, you will have to make continuous adjustments to your magnetic heading to keep the needle pointing to 0. As a result, your aircraft will travel a curved path to the station. If you want to fly a straight line, you can track a course using a technique similar to the one you used in VOR. Let's look at the procedure. Let's assume you want to track on the 240 degree bearing to the station, and a right crosswind has drifted you left of course. The ADF needle will point to the station which, in this example, is 5 degrees to the right. Turn right, using an appropriate intercept angle, and maintain that heading. In this case, a 20-degree correction angle is being used. The ADF needle will continue to point to the station. With the aircraft heading 260 degrees, the station is located 15 degrees to the left of the nose. As you approach the course, the ADF needle will continue to move away from 0. When the deflection equals the heading correction angle, you have intercepted the desired course. Here, the ADF needle reads 340, which equals the 20-degree intercept angle. When you have turned back on the desired course, it will be necessary to establish a crab angle to compensate for wind, in this case 10 degrees. Since the airplane is crabbing to the right to maintain course, the ADF needle will indicate that the station is to the left. As you get close to the station, the needle becomes more sensitive. It's important not to chase the needle or make large corrections during this time. Station passage is indicated by a reversal of the needle. The procedure for tracking outbound is similar to the procedure used to track to the station. However, the wind correction angle is established with reference to the tail of the aircraft. Some of the techniques you learned in tracking can be used to intercept a particular magnetic bearing. To understand the intercept procedure, let's assume you want to intercept the 60-degree bearing to the station. Your first step is to turn your aircraft to a heading that parallels the course you intend to track. Then determine whether the station is left or right of your aircraft by noting the direction the ADF needle is deflected. In this example, the needle is deflected 30 degrees left. If you turn left only 30 degrees, you will fly to the station, but you will not intercept the 60-degree bearing. A good rule of thumb is to double the number of degrees the ADF needle is deflected. A 60-degree intercept angle, in this example, means you will maintain a heading of north to intercept the bearing. When the ADF needle is deflected 60 degrees to the right, which is the same as the angle of intercept, you will be on the desired track. Remember to lead your turn by a few degrees to avoid overshooting the bearing to the station. Continue to track to the station using the same procedures we discussed earlier. Until now, we have taken a look only at the fixed card ADF indicator. The only difference between a movable and a fixed card is that you can manually rotate the movable card. This allows you to place your magnetic heading under the index at the top of the indicator. In this situation, the ADF needle automatically provides you with the magnetic bearing to the station. The tail of the needle provides the magnetic bearing from the station. Sometimes, when using ADF, the signal you receive may be erroneous or unreliable. If you are familiar with some of the limitations of this instrument, you may be able to avoid or minimize errors you might encounter. For example, reception capabilities for ADF facilities can vary considerably. To be sure you're receiving reliable information, always identify the station before use, then monitor its ident feature. If your heading indicator is not properly set to the magnetic compass, you may have problems with tracking and intercepting procedures. You should monitor these instruments often to ensure that the heading indicator has not precessed. Other phenomena that may cause erroneous readings in your ADF are twilight effect, thunderstorm effect, precipitation static, shoreline effect, and terrain effect. You'll learn more about these when you read your private pilot manual and study the operator's handbook for your ADF. ADF is just one instrument in your total navigation system. In many cases, it's possible for you to navigate using ADF alone. However, it is generally used with other instruments, such as VOR. In the next program, we will expand on the information already presented and see how it relates to advanced navigation.
Besides VOR and ADF, there are various types of advanced navigation systems and indicators available. Our purpose in this section is to introduce you to some of them and describe their capabilities. The first system we'll look at is area navigation based on signals transmitted by VORTAC, or VOR DME stations. As you learned earlier, VOR provides for navigation between stations. But VORTAC-based area navigation allows you to fly directly to your destination, often with considerable savings in time and operating costs. To accomplish this, a course line computer allows you to electronically relocate or offset navigation aids to a desired radial and distance from the original location. These offset stations are called waypoints. For example, assume you're planning a direct flight from Storm Lake Municipal Airport to Algona Municipal Airport, and you're using area navigation equipment. The first thing you must do after determining your route is to select the closest VORs to your flight path. In this case, they are the Spencer and Fort Dodge nav aids. Then establish waypoints along the route and determine the radial and distance each waypoint is from the VOR. Waypoint number 1 is 27 nautical miles from Spencer on the 140-degree radial. Waypoint number 2 is on the 335-degree radial, 23 miles from Fort Dodge. These values are then entered into the receiver prior to your departure. Now you can simply fly from waypoint to waypoint until you reach your destination. Your course information is displayed on the VOR indicator just as it is in normal VOR navigation. If you drift off course, the CDI points toward the desired course. However, the deviation is indicated in nautical miles instead of degrees. The mileage that each dot represents is determined by the manufacturer. Now let's look at another form of area navigation called long-range navigation, or LORAN. This system also lets you fly directly to your destination, but with LORAN, you don't have to create waypoints. Instead, it uses a network or chain of stations which transmit low-frequency signals in the 90 to 110 kilohertz range. These low-frequency signals follow the contour of the Earth in the form of a ground wave and have a reliable reception range of 600 to 1,200 nautical miles. LORAN transmitters can also produce sky waves which increase the reception range, but these signals are not considered reliable for navigation. In a typical LORAN chain, there is a master station and 2 to 5 secondary or slave stations. The master station first transmits a coded pulse group. Then, each secondary station transmits its pulse at a specific time interval after the master pulse. A LORAN receiver in the aircraft determines your position by measuring the time difference between the receipt of the master pulse and that of the secondary stations. Your position is then translated into latitude and longitude values and displayed on the receiver. After you enter the destination, the receiver displays course and distance to the specified point. During the flight, it provides a continuous update of the information. Because LORAN operates in the lower frequency range, electrical disturbances such as lightning and precipitation static can cause signal loss or distortion. For this reason, aircraft with LORAN units should have static discharge wicks and bonding cables to help dissipate any static buildup. Another limitation is the variation in speed at which the radio signals travel. The surface type, foliage, and seasonal changes can affect the speed of the radio waves and decrease their accuracy. There are several types of LORAN units available, and their capabilities vary considerably. Besides bearing and distance, some receivers provide wind direction and velocity, fuel consumption, and other types of information. You can determine the features and limitations of the particular unit you're using by referring to the owner's manual or to placards located on the instrument panel. Another type of navigation that is quickly replacing traditional ground-based navigation systems is the Global Positioning System, or GPS. This type of navigation system relies on signals received from satellites to calculate the position of the aircraft. A GPS receiver determines an aircraft's position through triangulation of distance measurements from a minimum of 3 satellites. And because this system is satellite-based, it doesn't have the limitations that a ground-based system might have. It provides the same benefits as other point-to-point navigation systems, but with unmatched accuracy. 95% of the time, lateral position accuracy is within 100 meters of the true horizontal position. GPS receivers incorporate a wide array of navigation capabilities that help increase situational awareness, such as moving map displays and the ability to select the nearest airport. With such a wide variety of manufacturers and options comes the responsibility to understand the operation and limitations of the system you use. Your pre-flight preparation should include a review of GPS and how your particular system functions. GPS units come in both panel-mounted and handheld units. Handheld units are meant only for flight under VFR conditions and are not certified for use under IFR conditions. Each GPS unit has a different type and location of the receiver antenna. Panel-mounted GPS units have permanently affixed antennas. A handheld unit, however, may have a self-contained antenna or a detachable antenna. You need to make sure these antennas are in a location that provides adequate signal reception. It is also your responsibility to verify that a panel-mounted unit has been properly installed and maintained in accordance with the AFM or POH. You should also be aware that GPS systems utilize Receiver Autonomous Integrity Monitoring, or RAIM. RAIM checks the integrity of the navigation solution and alerts the GPS user to a position error. Many handheld GPS receivers do not have RAIM alerting capabilities. These receivers should not be used as the sole system of navigation. Instead, you should integrate GPS with other forms of navigation, such as VOR, pilotage, or dead reckoning, to ensure navigation accuracy. Most GPS units include a navigation database. Flying with an outdated database is like using an expired sectional chart. In fact, to fly IFR by GPS, you must have a current, updatable database. Since both airspace and navigation data are constantly changing, you should apply this requirement to VFR GPS use as well. GPS is rapidly becoming the standard means of navigation. Take the time to become familiar with the unit you will use, planning your flights carefully prior to departure, and when possible, programming your GPS on the ground. In addition, always check NOTAMs for any outages in the GPS system that would affect GPS navigation. Another way to increase your navigation capabilities is through use of specialized instruments. One such instrument is the Horizontal Situation Indicator, or HSI. It combines the functions of two instruments in one display. Its movable compass card works like a heading indicator to give you magnetic heading information. The other elements work like a VOR indicator to help you maintain your orientation to the station. Let's take a look at the components to help you understand the capabilities of HSI. A heading select bug is an index that rotates when you turn the heading select knob. If an autopilot is engaged, the airplane will automatically turn to the heading you select with the bug. If an autopilot is not used, the select bug serves only as a reference marker as you complete the turn. Like the CDI, the lateral deviation indicator tells you if you are left or right of course. When you are on course, the needle is aligned with the course arrow and the reciprocal course pointer. The ambiguity indicator works like a to/from indicator to tell you if you are flying to the VOR or from it. One other feature that HSI provides is glide slope information, which is used during instrument approaches. You may learn more about this if you proceed with additional pilot training. Now let's look at another advanced instrument, the radiomagnetic indicator, or RMI. The RMI combines the functions of three instruments: the heading indicator, the VOR indicator, and the ADF indicator. The slaved compass card automatically displays your magnetic heading at the top index. Typically, the single needle indicates the magnetic bearing to the VOR station, while the double needle shows the bearing to the NDB. The tail of each needle indicates magnetic bearing from the station. With the needles indicating the bearings to separate navigation aids, constant position orientation is provided. You can track toward one facility while monitoring your progress on another. The information presented in this section is intended to serve only as an introduction to advanced navigation. Be sure to refer to the operating handbook for details on the system you are using.